Allora, buon pomeriggio a tutti, benvenuti a questa scuola del progetto europeo Heracles. Una breve introduzione con un paio di saluti istituzionali. Io dico due parole di introduzione a valle dei colleghi che porteranno i saluti e che quindi mi precederanno, che sono il professor Gigliotti, vice direttore del Dipartimento di Ingegneria Civile Ambientale dell'Università di Perugia, e il professor Pane, che è qua non solo come collega professore dell'Università di Studi di Perugia, ma anche in rappresentanza della fondazione dell'Ordine degli Ingegneri, che oggi riconosce crediti formativi ai suoi iscritti per chi partecipa a questa iniziativa. Allora io darei subito la parola al professor Gigliotti e poi al professor Pane.
Grazie al professor Ubertini. Benvenuti a tutti. Io credo che questa sia un'occasione molto importante sotto tanti punti di vista. Molto importante perché ci stanno molti studenti di lauree magistrali sia di Perugia, il professor Ubertini anche di fuori Perugia, ci stanno studenti di dottorato di ricerca, ci stanno postdoc e ci stanno liberi professionisti, quindi significa che l'interesse che questa scuola ha destato è veramente molto grande e molto importante. Questa scuola è strettamente legata e correlata con un progetto di ricerca europeo che sta portando avanti per la sede di Perugia il professor Ubertini, ma è un progetto, essendo un progetto europeo, chiaramente ci stanno anche molti altri partner europei. Però mi piace sottolineare una cosa: penso che sia un percorso virtuoso questo, che dovremmo cercare di seguire un po' tutti. Questo progetto europeo da Perugia è partito da un progetto molto locale, perché prima di aver finanziato il progetto europeo il professor Ubertini ha avuto finanziato un progetto della Fondazione Cassa di Risparmio. Su che cosa? Proprio sul monitoraggio dei monumenti, quindi di qualcosa di storico. Quindi è partito da Perugia come monitoraggio, se non ricordo male, di San Pietro, della Fontana Maggiore e della Basilica, e finanziato da una piccola fondazione, la Fondazione Cassa di Risparmio di Perugia. Evidentemente anche una piccola fondazione in grado di vedere le potenzialità di un gruppo di ricerca, che partendo da questo piccolo poi è arrivata a farsi finanziare un progetto europeo. Quindi l'idea è molto innovativa, l'idea è molto bella, e sicuramente durante questa Winter School, che è un po' però a metà strada tra una winter e una spring ormai, siamo nella settimana che ci porta a primavera, riprendendo le cose serie, è molto importante, è stato questo grande interesse. Di questo, come vice direttore del Dipartimento, ne sono molto contento. Chiudo questo mio intervento portando i saluti del direttore del Dipartimento, che oggi aveva un altro impegno istituzionale, e di tutti i colleghi del Dipartimento di Ingegneria Civile ed Ambientale, e un particolare ringraziamento anche all'Ordine degli Ingegneri, qui rappresentato dal collega Vincenzo Pane, che ha fortemente creduto evidentemente in questa scuola, tanto da permettere l'acquisizione di crediti formativi professionali per gli iscritti all'ordine professionale. Grazie ancora.
Grazie molto professor Gigliotti. Adesso passo la parola al collega professor Pane per i saluti.
Grazie, ringrazio Lucio Bertini per questo invito. Oggi appunto per chi di voi non è di Perugia, sapete che Filippo fa parte di un'industria familiare, tutti i professori universitari e di accademici. Scusami Filippo. Dicevo, sì, io sono qui in rappresentanza del Consiglio dell'Ordine degli Ingegneri e della Fondazione dell'Ordine degli Ingegneri di Perugia, che promuove la cultura in campo ingegneristico. ci saranno 3 crediti formativi per la sessione di oggi e anche 3 crediti per quella di domani, che è dedicata più agli aspetti ambientali. Quindi mi chiedevo se c'è qualcuno in rappresentanza, se c'è qualche collega iscritto all'ordine degli ingegneri in questo momento. Sì, ce ne sono alcuni, molto bene, per piacere, mi raccomando poi di formalizzare quanto dovuto. Io voglio dire 2 parole. Il professor Gigliotti ha detto che è un tema importante, questo è un tema importantissimo per una regione come la nostra, di assoluta interdisciplinarietà. È significativo notare che tutti i candidati rettori ora a questo Ateneo, ne sono tanti, stanno tutti puntando sull'interdisciplinarietà, perché anche a livelli di finanziamenti internazionali ormai, se non si associano le aree scientifiche alle aree cosiddette umanistiche, ci sono poche speranze di avere finanziamenti importanti e di risolvere, di dare un contributo ai problemi importanti del nostro pianeta. Tra i problemi importanti c'è il patrimonio culturale, c'è quello ambientale di cui si parlerà domani. Peraltro c'è qui, non so se lo sai Filippo, c'è la CERE, c'è anche un gruppo di ricerca recentemente fondato, il coordinatore il professor Gamellotti, perché ha lavorato molto sui beni culturali, il quale ha formato un gruppo per la ricerca per la resilienza del patrimonio dei beni culturali. Quindi dico soltanto una, c'è di necessità di interdisciplinarietà, le discipline coinvolte sono quasi innumerevoli, perché evidentemente ingegneri, architetti, storici dell'arte, restauratori, ma anche nel campo della sicurezza, evidentemente geologi, pianificatori, tecnici della protezione civile, eccetera, eccetera, eccetera. Quindi assolutamente interdisciplinare. Soltanto purtroppo c'è ancora un po' di difficoltà a vedere questo come una sinergia. Molto spesso viene vista come un'invasione di campo di alcune competenze, di alcune professionalità rispetto a altre. Questo va assolutamente superato, è un concetto ormai antico. Ci sono alcune lobby di tutte le professioni che cercano di tenere sotto le proprie braccia questi argomenti, ma queste sono cose che evidentemente hanno bisogno di un approccio scientifico interdisciplinare. Abbiamo aperto quest'anno a Foligno un corso di laurea magistrale in ingegneria della sicurezza che si chiama Protezione e sicurezza del territorio e del costruito. Bene, sappiate che il nome originale di questo corso di laurea è la protezione e sicurezza del territorio e dei beni culturali. Soltanto per le questioni alle quali accennavo poc'anzi, poi sono state date indicazioni da parte dell'ANVUR, che doveva ufficializzare e promuovere il corso, di eliminare la dizione beni culturali perché è di competenza degli architetti e dei restauratori. Sebbene è evidente che la sicurezza, soprattutto quella sismica di cui si parlerà ampiamente oggi, deve essere competenza degli ingegneri, che devono lavorare in sinergia con gli altri tecnici e professionisti di cui parlavo. Quindi io penso che ci sia tanto lavoro da fare in questo campo e questo evento testimonia la necessità di questa attività. Grazie.
Ringrazio anche il collega professor Pane, mi associo assolutamente alle sue indicazioni sulla importanza della multidisciplinarità in questo campo. In questo senso il progetto Heracles, a cui ha accennato il professor Gigliotti, è un esempio di progetto multidisciplinare e ne avrete un po' un assaggio in queste 2 giornate. Fatemi dire qualcosa sul lato dell'Università di Perugia. L'Università di Perugia partecipa come partner, questo progetto è un progetto che ha 16 partner, poi tra poco sentirete l'intervento della coordinatrice del progetto del Centro Nazionale delle Ricerche. Perugia è uno di questi 16 partner e uno dei 3 partner del progetto che appartengono alla Regione Umbria, perché in questo progetto è presente, oltre all'Università di Perugia, anche il Comune di Gubbio e un'azienda eugubina che si chiama CQR. Quindi sui beni culturali fatemi dire che l'Umbria è stata sugli scuri nel momento in cui questo progetto è stato finanziato. Il progetto è stato finanziato nell'ambito del programma Horizon 2020, di cui tutti siete a conoscenza. È inutile dire che si tratta di progetti molto competitivi. L'acquisizione di questi finanziamenti è veramente complicata. Sul lato Università degli Studi di Perugia siamo di fatto due strutture operative che partecipano a questo progetto. C'è il Dipartimento di Ingegneria Civile Ambientale, a cui io appartengo, e c'è il centro CIRIAF, il centro di ricerca sull'inquinamento da agenti fisici e atmosferici, che segue gli aspetti più ambientali. Quindi diciamo questa multidisciplinarità del progetto l'abbiamo riportata anche a livello locale, a livello dell'Università degli Studi di Perugia. Nel ringraziare tutti i relatori che interverranno quest'oggi, poi via via che li introdurrò li ringrazierò di nuovo. Ringrazio tutti voi che siete venuti a sentire i lavori. L'ultimo pensiero va all'aspetto dell'importanza dell'argomento non solo dal punto di vista dei beni culturali, ma in Heracles si parla di resilienza dei beni culturali esposti ai rischi legati al cambiamento climatico. Poi in questi 2 giorni noi allargheremo lo sguardo, perché ovviamente ci sono relatori che provengono da altre esperienze, come anche nel nostro caso il mondo del rischio sismico, dell'ingegneria sismica, a cui già accennava il professor Pane. Il tema del cambiamento climatico è quanto mai di attualità. Oggi è la prima giornata lavorativa che segue la giornata del 15 marzo, che è la giornata mondiale sul clima, e sapete quanto l'argomento sia d'attualità. Bene, il cambiamento climatico impatta negativamente anche sui beni culturali. Con questo io chiuderei la sessione dei saluti e darei inizio ai lavori. Grazie. Allora, questa scuola è una scuola internazionale, per cui i lavori si svolgeranno in inglese. La sessione di saluti iniziale l'abbiamo fatta in italiano, ma d'ora in avanti le presentazioni saranno in inglese, per cui adesso invito la relatrice, la dottoressa Giuseppina Pareletti del CNR, a fare la sua presentazione, e ve la introduco brevemente in inglese. Dr. Giuseppina Padeletti from CNR, the institution that coordinates. We'll solve this issue. For some reason, what we saw on the screen here was not what was projected here, so don't ask me why. So Dr. Giuseppina Padeletti is the coordinator of Heracles project, and she will give a speech on the project itself and on the mission and vision of the Heracles project. Thank you, Giuseppina.
Thank you, Filippo. Thank you to the University of Perugia to be the guest of the Heracles Winter School 2019. This is the 3rd school that the project is organizing. So my job today is to show in general the mission and the vision of the project, because you will have in these 2 days the opportunity to go deeper in the activity of the project through the presentation of my colleagues, the other partner. Heracles stands for resilience against climate events on site, and the aim of the school, of the Heracles school, is then to provide information to the people here, students, scientists, civil societies, professionals, about the skills that are present in this project and the activities that we have carried on. Another scope of the activity of the project that is also very important, that will not present here, but is also to represent a big part of our activities, is to increase the societal awareness towards the importance of the cultural heritage preservation, and also about the importance of the climate change effect. So in terms of increased resilience. And I think that a school should also have this object. As you know very well, nowadays the integrity of the monuments of the archaeological site and of all the city and town is increasingly threatened by the climate change effect and its extreme meteorological phenomena. Also, 2 days ago, there was a big storm happened in different regions of the world. And if it impacts severely on buildings, on modern town, the cultural heritage monuments, of course, are exceptionally vulnerable to this threat. And we have to consider, take into account that they have a very high cultural importance because they are a source of information about our past and represent a symbol of identity for the community where these cultural heritage assets are located. And we have also to consider the negative impact that the local community can undergo, also in terms of the socio-economic effect. And we are referring to the tourism and satellite activity. So it is very important to protect our cultural heritage. With this scope in mind, the Heracles Consortium was built up, made by 16 entities from 7 European countries. Among the partners there are universities, there are research institutions, big industries, small medium enterprise, international organization, superintendencies, and last but not least, the end users, that for us are, in this case, the municipality of Perugia and the superintendencies of the Ephorate of Antiquities of Heraclion, and that is the correspondent of the Italian superintendencies. The country that we choose as object of our study were Italy and Greece. Why we choose these two countries? Because the majority of the worldwide cultural heritage is located in these two countries, and their ancient civilization, without that, are considered as world heritage. But these two countries are also characterized by similar risk exposure that we will see in a while. Another choice that we made was to focus on living areas, let me say minor living European areas. We are not referring to Venice, Rome, Florence, but we choose minor centers because anyway the European countries are constituted by minor centers that often are not really taken into account, but they are constituting the essences of our countries, our culture, and our identity, and above all our economy, where people live and work. About the risk, you can see on the left the rainfall map erosivity. That is a database dated from the European Commission, and the part in blue are the most affected by the erosivity created, of course, by heavy rainfall. And as you can see, the Mediterranean basin is the area most affected, Italy and Greece. If we consider also the seismic risk, again, the area in dark red and brown are the most affected. And again, we have Italy and Greece. So to go to see which are the test bed and what we have observed in these two countries, we have in Greece, in the island of Crete, in Heracles, we choose the Minon Palace of Knossos, also because this palace, this location, represents the center of the first civilization of the Mediterranean basin, that we can consider the first European civilization. And it dates back 2,000 years before Christ, so 4,000 years. It is very impressive if you see what they were able to produce at that time. And also we studied the Venetian fortress of Cules, that is in the port of Heraclion, and the study of this fortress that is in the port, in the sea, want to symbolize all the monuments that are located along the coast of Europe and that are facing the risk of hazards from the sea, significant impact from the sea. So we are referring to sea level rising, increasing intensity of extreme weather phenomena as a storm. You will see some photo about that. The increased salinity that is accelerating corrosion of materials and of the structure. And in Italy, we choose Gubbio, that is, located in Umbria, along the Apennine Mountains, and this town wants to represent all the historical monumental towns in Italy, but also in Europe, that were conceived and built in the past, when the climate was very different from nowadays, and now they suffer a lot to face with the effect of the climate change. And here we are referring to the hydrogeological risk produced by heavy rains that are producing flood and landslide and so on. So the tweets that we can list in some way as fog, storms, sea waves, effect linked to temperature variation, humidity, variation of the humidity of the air, pollution and others. Why impact on the structure? Because they can create structural instability, material degradation, corrosion and others. So in periods like nowadays, when there are governmental budget constraints limits the mitigation strategies, it is very important to have a tool for available a tool for an effective management of this matter, for cost-effective maintenance and restoration. And in this area, the Heracles project decided to contribute. What we have done, of course, at the beginning, we have, first of all, performed an investigation on site, and on the basis of this investigation, and also on the basis of the end-user requirements, namely the Equator of Antiquities of Heraclion and the Gubbio municipality, it was very clear that one of the fundamental elements is to have available an integrated system of technologies for monitoring. So we organized the activity of the project, starting from wide area monitoring. I cannot imagine something more wider than the satellite observation, till the observation of the site of the monument, till the single element constituting the monument, including the territory where the asset is located. Here you can see the concept of the ICT platform that is one of the core of the outcome of the project, that is developed by the big industries present in the consortium, that is intended like a container, let me say, where are inserted all the information on the site and on the monument coming from what are called the context analysis, the site health analysis, and the risk analysis. Of course, all these activity provide information on the multi-risk affecting the asset, and this kind of activity provide a lot of multi-source data, creating many useful information directly available for the end users. Of course, the ICT Heracles platform, that is one of the core of the product that we are providing at the end of the project, is intended to be flexible, to guarantee a general applicability. Why will be flexible? Because it's depending on the monument you have, depending on the requirement the monument has, depending on the specific context, site health and risk analysis you will do, the platform will be tailored on the specific and user requirements. To illustrate again in a visual way the concept of the project, we start from the wide area observation, coming literally also on the field for other investigation, and then performing the in situ analysis, and to go more in depth, sometimes, as I would say very often, we have also carried on ex situ analysis in laboratory with minimally damaging sampling, of course, of the monuments itself. So, from all these activities, namely context and site analysis and risk assessment, the answer that we are able to do are monitoring and preservation action to contribute to best practice in pipeline. We have studied the old materials to propose, we are proposing a new material and a solution for restoration and conservation. Of course, we are talking about the materials that are characterizing the monuments that we have studied. And last but not least, as I have already said, there is also an important activity that is concerning the safeguard and valorization of the cultural heritage through the promotion of the social and economic value of this asset of the communities. And this part is also related to what is called RRI, that means responsible research and innovation. That is very important in the programs from the European Commission nowadays. So what we are studying in activity. Of course, I am presenting really in a general way many activities that you will see more detailed explained by the partners that will follow me. And here you can see what it was possible to obtain from the monitoring from satellites. It was possible to obtain the maps of displacement in time. that are described from the green, in this case, points, and the color of these points have an intrinsic meaning related to the stability or not of the structure and the areas. But I think that immediately after me you will have the opportunity to go deeper in this matter. The Heracles fortress is located in the sea. Here I reported some images, real experienced by us, because it was a storm occurred in October 2016, 2 days before our meeting that at that time was held in the Heracles fortress. So at the last moment it was not known if it was possible to exploit the meeting there. And so you can see how severe is the effect of the waves against the fortress, and not only of the fortress, of the sea, but also you can see in the yellow circle there is a piece of rock that is coming from the breakwater structure that, of course, was intended to put in front of the fortress to defend the fortress from the sea, but in fact, when the storm becoming more severe than in the past, the breakwater structure are also problems because are going against the fortress, creating damages. So we have classified in the different areas of the fortress depending on the risk. Moreover, there is an activity concerning the deployment of oceanographic sensor in front of the fortress, registering the water level and the sea temperature, and then these data are of course elaborated to measure the intensity of the waves. Here you can see instead the meteoclimate data platform. The form that you are observing is the island of Crete with the precipitation image and the time series of the surface temperature that you can see here in order to perform long-term assessment of the climate evolution. Material degradation phenomena, and you will see as well, a colleague of us we present the part about the long-term effect of the climate change. The material degradation phenomena, I suppose that are very clear also from these images. So you can see the corrosion of the stone. If we move to Knossos, we can see that there are major cracks present in the structure, and there are also examples of insufficient bonding between stone blocks in the masonry elements. Again, to show some phenomena of degradation of the materials, you can see some photo. Moreover, Knossos Palace is an emblematic cultural heritage asset because, we will see more in detail, it was reconstructed at the beginning of the 20th century by Sir Arthur Evans using concrete. So it is, I can say, a unique opportunity, studying something at the beginning very ancient, but that present important problems that the concrete of 100 years ago present. Moreover, there are also the difficulties linked to the fact that elements built in concrete are over other materials that were pre-existing and characterizing Knossos, as for instance the mineral gypsum of selenite, which is a spectacular material but very, very different from concrete. So, This is in fact, the mineral gypsum. The first image is the mineral gypsum that has not undergone other changes. In the second one, is the mineral gypsum is translucent, is like alabaster, and in fact it was supposed that the use was linked to the light effect produced by the sunshine in some part of the palace. But then, due to fire and also other degradation phenomena, the secondary gypsum is developed from the primary and is losing its beautiful appearance. For this part, consolidants were developed. To remain in the concrete domain, you can see very well how is degraded, the structure in Knossos Palace. Still some photo, you are engineers, so you can see very easily where are the problems. So in this case, there were problems to solve, also in terms of thinking about new solution for restoration. And so we developed, but it will be object for another presentation, some mortars specifically dedicated to concrete mortars and to mortar for Perugia. Here we are experimenting some materials. Another important product, let me say, of the project is to have generated what we are called the general protocols. What we have to do when there is a problem on a monument. So this is a general protocol, and the monument is symbolized in the center. You will see that depending on the problem that the monument presents, you have the recipe of the action to perform. So satellite that are providing information through the radar sensor, optical sensor, and multispectral. Of course, the data meet models. Then there are the activity linked to the in situ and ex situ analysis that can help also in design new material for mitigate the end, for restore and mitigate the effect of the climate change. Here just a quick view from the general. Of course, it is possible to derive the specific, the systematic protocols for the monument. So this is the protocol for Pules, for Knossos, and you will see also that we have developed that for Gubbio. What we are studying in Umbria, in Gubbio. In Gubbio, Palazzo dei Consoli and the town walls, le mura pubbliche, are object of the study. The climate change, you can see some images very clear. This is an area where you can park if you come to visit Gubbio. Is il parcheggio del seminario. And the photo was made, the photo in June 2013, is the same area in the first 2 or 3 days of distance between them. So in one case you can park your car, in the other one, absolutely not. The other image that appeared to be a photo taken in winter, instead was characterizing May 2016. So it is clear that something is wrong. To study the long-term meteorological behavior, we have used, in collaboration with, we used the data of the ARPA meteorological station located in Italia for the long term. Then with the University of Perugia, we performed also other kind of meteorological study or climatic study on more local meteorology. About Palazzo dei Consoli, of course, we have the same maps of displacement in time. that will be described by the colleagues of IGEOS, and some interesting critical aspects were found also together with the University of Perugia for the structural assessment. The status of the facade was also done through the method of the material degradation and the cracking. The structural evaluation was carried on through the positioning of accelerometer and the linear variable displacement transducer in different parts of the palace. You will have for sure the opportunity to hear from Professor Berti details. We performed also the ground penetrating radar inspection. This is an important technology that we can gain information about the internal structure of the wall, and because it is possible to put in evidence the presence of cavities and cracks that apparently are not appearing. Was done an evaluation of the material degradation through the use of different techniques. From structural, I am a chemist, so I'm not talking about the structural stability, but the structural of the compound. We have used X-ray diffraction, different kind of microscopies, and to assess the chemical, physical properties of the materials. For the town walls, I can show some photo about collapses and chasms that occurred in the last 20 years very, very often, creating problems, as you can see. Still collapses and chasms along the street that is coming to the mountains. And these are still problems remaining in a wide part of the wall nowadays, in which the external part is lacking and is exposing the internal part of the wall that is even more easy to degrade from the UV rays. Still some images. Of course, also from this area was possible to obtain the maps of displacement in time, even if some difficulty arises from the presence of vegetation. Were identified 4 areas, most critical areas. Digital survey from aerial photos through a drone were carried on. To study degradation, also here and these images were very useful to identify critical zone. Inclinometers were located for structural evaluation in different parts of the walls. Not just to say, every one of us know that in the important structures in Italy, the inclinometer were lacking. And in this town the mechanical properties of the wall and the mortars constituting the walls were carried on with the inclinometer test and the mechanical test in the lab. And the study of the material degradation were also carried on through the use of many analytical techniques. So I would like to acknowledge, to close with an acknowledgement to all the consortium, because really this partnership was a very strong partnership with a very strong partner with an excellent experience and skill. And by the way, it is also important to cite that this project was chosen by the European Commission as a story of success. You can also see some detail. There is a particular session on Cordis on a successful story, and we are there. So, really, I would like to close with a message, thanking also, of course, the audience, that I hope that are interested in this domain. And I would like to close with a message, because only in the Heracles countries, Italy and Greece, there are 69 UNESCO World Heritage Sites in terms of tangible sites. Of course, in all Europe, much more, probably not much more because the concentration is more. So we have, I think, a big responsibility because this represents a vulnerable European heritage at risk and we have to preserve it. We can follow our works and activities on the project website and also on Facebook and Twitter. I don't know if we have time for this movie. We would like to show to you a movie that was realized not by us, in fact it's a professional one, but by the European Commission that asked it. So,
Old town quartiers like here in Gubbio, Italy, are a source of local pride and an irresistible tourist attraction. But are we in danger of losing this historic heritage to climate change? The 14th century Palazzo del Console is one of Gubbio's most iconic buildings, hosting art and archaeological exhibitions. But the cracks appearing in the stone walls are raising concern that the ground under the Palazzo may be shifting. This could be caused by climate change, as rains are becoming stronger and more frequent. The city takes this threat very seriously.
Gubbio is a city made of stone. It's an element that's most precious to us. We have to keep it under control.
Scientists from Heracles, a European research project, are studying the effects of climate change on ancient monuments. Their methods range from using satellites that monitor ground shifting to taking samplings of walls, like this test with a pressure-sensitive drilling tool.
First of all, this sampling shows how hard the stone is. After this, a chemical analysis of the drilling residue will reveal the mineralogical composition of this stone. It will show possible products of erosion, like soluble salts.
Gubbio knows very well how rain can bring down stone walls. In the past, parts of the ancient city's defence perimeter have already collapsed under the weight of shifting ground. Grains have weakened the mortar, and stones are falling out. What remains of the city is now carefully monitored.
Over the past 3 years, we had a lot of extreme weather. The precipitation was much above average. This is affecting the wall structures that we need to maintain.
Gubbio isn't the only place where scientists are working to understand the climate threat. Climatic fluctuations are particularly menacing in coastal towns, rich with monuments such as Coulis, the Venetian fortress in Crete. For a deeper understanding of what's going on, let's join scientists in the Mediterranean Sea. The waves hitting the 16th century fortress are constantly eroding its walls. Changing climate shifts the wind direction and the pattern of waves. What does this mean for stone structures? Some clues may be found at the seafloor. These researchers are using sonar to find out how the sea is affecting stones underwater.
This sonar allows us to see what's happening on the sea floor. On the scans, we can clearly see cavities in underwater fortifications. Through repeated surveys of this area, we can observe how these cavities are evolving with time. This way, we can keep tabs on the erosion.
At the seafloor, the researchers have installed sensors that are continuously recording water temperature and wave height. Twice a year, scientists dive to retrieve the data from these sensors.
We need this data for our digital model to see how waves affect the Coule's fortress. We need to know the wave energy the fortress receives. By combining this with past measurements, we can make short and long-term projections and see how this is evolving due to the effects of climate change.
After the data has been copied, researchers place the sensors back on the seafloor for another 6 months of monitoring. Some of the effects can be detected inside the fortress. This instrument flashes a powerful laser on the wall surface, turning its particles into plasma that can be chemically analyzed.
The sodium chloride salt accumulated in the surface. This is one type of accumulation from the sea, but also the water penetrates the gold and changes the chemical structure of the rock, and this also affects significantly the monument.
Local authorities use the data collected by scientists to get a better idea of how to maintain this site. There are concerns that with climate change, old stone buildings will degrade faster, making their upkeep more expensive.
We have already conducted a large restoration campaign here. Our aim is to keep monitoring the building to see if and when more measures will be needed. Our ultimate goal is to find a way to protect this monument for the next 500 years.
The Knossos Palace, site of the Minotaur's Labyrinth, was partially restored 800 years ago with reinforced concrete. Climate extremes have weakened the cement, causing the iron to rust. To preserve this site, new types of cement and mortar are needed.
Our research project will help to create new materials and make them available to restorers, so that we'll finally have a solution suited for this particular monument. This will help us to better protect our heritage.
Scientists have developed a new mortar adding nano and microparticles that improve weather resistance. And there's a new cement, which is similar to the one used originally, but less porous, so air can't penetrate it as easily.
Quindi è un risultato pratico, trasferibile.
These practical results can be used directly at this archaeological site, one of the most important, most significant in Europe, the site of the first European civilization in the Mediterranean basin.
Europea del bacino mediterraneo.
From planetary scale climatic changes to microscopic specks of dust, scientists are fighting battles on many fronts to defend the heritage of our art and history.
Thank you very much, Giuseppina, for your very interesting presentation. We are a little bit out of schedule, but not much, so we will save a little bit of time during the break. Now is the time of the talk that was scheduled to be given by Dr. Mario Costantini from Egeos. Instead, Mario could not come, and there is his colleague, Dr. Salvatore Falco, that will give a speech on together with Mario. You heard from the presentation of Dr. Pareletti that in the project there are there is a big part that is devoted to satellite radar interferometry, which is a pretty interesting monitoring approach that for us as engineers looks quite promising, and we will learn about the results achieved through this technique within Heracles in the sites of the project. Okay.
Good afternoon to everyone. Let me first thank Professor Ubertini for inviting me to this school, and we collaborate within we are partner of the Heracles project. We collaborate in particular with the University of Perugia and for the Gubbio site, so we are quite interested in this dissemination, of course. The title of this presentation is Satellite Radar Interferometry, Introduction and Application to Building Structural Assessment, because satellite radar interferometry, we believe it's a powerful technique to monitor the ground, the territory, in particular infrastructures and buildings, and as we saw during the project, also the cultural heritage sites. So I will begin by explaining a bit the basic principles of the satellite interferometry. This is a technique which is very powerful, but is very different from other measurement techniques. So it takes some caveats, some attention to understand what it does, what it actually measures, and so the meaning of the results that I will show you. So I will also explain to you the potential and the limits of this technology, of course, and show some general examples of different kinds. Also, I will show you more in detail what Dr. Padretti showed briefly before, the results of the analysis on in particular of the Palazzo dei Consoli in Gubbio and the Knossos Palace and the Fortress of Koules in Crete. And at last I will summarize rapidly something that we learned within the Heracles project, that is a possible methodology that can be applied to perform monitoring of structural stability. We developed this methodology for cultural heritage sites within the Heracles project, but this can be extended also to other buildings and infrastructures and so on. So very quickly, not very quickly, what is SAR interferometry? First of all, SAR stands for synthetic aperture radar, so it's a kind of it's a technology, a radar technology. Those are two satellites that are moving above a mountain that is the target of the observation. They have a radar on board that is taking quote-unquote pictures of the scene below, and by using a interferometric approach to the images that they acquire, it is possible to reconstruct the information related to this mountain or the observed scene. More in detail, what happens? Okay. What happens is that this technology is able to measure very slow movements. You will see later on that we are talking about tens of millimeters per year. This is the frame of the idea. So it's slow movements of the surface of the observed scene, which can be either the slopes of the mountain or infrastructures or buildings and so on. When the satellite passes on the scene, it acquires an image of the scene. It's a two-dimensional image. It's actually, let's say, it's a photography. It's not optical. It's radar. At the later, let's assume that there is a substance, which in this case it means just a movement of the observed scene. And at the second time, the satellite passes again and takes another image, acquires another image. You can see that the second the path of the electromagnetic wave of the second satellite is a bit different from the first one. And by combining these two information, it is possible to understand what happened. Why? Because the difference in the path that is indicated in the top between the two positions is actually due to three possibilities. A difference in position of satellite, the first one, the presence of atmospheric screen, so clouds and so on, and the movement of the observed scene. We are interested, of course, in the movement of the observed scene. We know more or less what the position of satellite. We don't know the contribution, the atmospheric contribution. So we'll go quickly here, but we need, last line, multiple acquisitions on the same area, acquired at several days of distance one another, to understand what happened on the ground and measure a displacement evolution of the observed scene. Just to let you know what we are talking about, general idea. This is a powerful tool because since these sensors are mounted on satellites, we can monitor very large areas. Okay, we can go from very large areas. In this case, we'll see that we go till the single cultural heritage site. But first of all, an important concept: satellites have polar orbits usually, which means that they either go from south north, or this is called ascending orbit, or from north to south. This is the descending orbit. They can look sideways, so to the right or the left, and this means that they are very sensible to displacements, movements that are in the vertical direction or in the east-west direction. They are less sensible to movements north-south. Also, the slope of the observed scene has a meaning. Let's imagine that this is a satellite and it's observing a valley, and two slides of the valley have those movements, the orange one, which are two landslides, okay, that are converging toward the bottom of the valley. If you look at from the side, if you look at the landslides, they are going downwards, of course. Most landslides do that. But from the satellite point of view, the left landslide is actually, it measures only the projection of the movement towards along the line of sight. So it sees a downward movement, the red one. On the other, for the other landslide, it actually measures an upward movement because that landslide is moving towards the satellite. It's the blue contribution. So it's important to have also the other geometry, acquisition geometry. This is the descending one. For this one, the observed scene will be the opposite. The left landslide is going upward and the right one downward. This is important. Later on, we will see some results to understand what's actually happening. So what are the applications of sun interferometry regarding monitoring of terrain and structural deformations? There are a lot of applications: subsidence phenomena, landslides, as we've seen, volcanic phenomena, and the earthquakes, mining and underground excavation, oil extraction, monitoring of highways, viaducts, railway infrastructures, pipeline, or other structures such as dams and industrial sites, and last but not least, building monitoring, building stability monitoring, of course. An important concept is that what we are looking at are particular features of the observed scene, of the ground of a building, that are called persistent scatters. Persistent scatters are structures that reflect the incoming electromagnetic wave always in the same way, in a coherent way, and are stable in time. For these persistent scatters, we can, for example, in this picture, I don't know if it's clear, but there is an optical image, and superimposed there are several points, colored points. Each point is a persistent scatter, and its color is connected to its mean velocity in millimeters per year. So we can detect the persistent scatters, locate them in 3 dimensions, measure their mean velocity, So in this case, a red point means that the mean velocity that is more than 22 millimeters per year going away from the satellite. A blue point would mean towards the satellite. A green one means it's stable. It's stable within 2 millimeters per year, plus minus 2 millimeters per year. But it's also possible for each of these points to measure its displacement. We acquired 30 images, several acquisitions. So for each of them, we can measure the relative displacement of that persistent scatter during the time. So we can know exactly its history. Of course, this is not a continuous measurement because we can have a measurement every time we have an acquisition, but it's still useful. What kind of scene can we observe? Well, this is Piazza Plebiscito in Naples, so an urban area, and you can see in 3D scene. The previous one was 2D scene. Here you can see that the persistent scatters gathers along the sides of the buildings, where they find triedra and diedra. On the roofs, they don't gather. We don't detect many persistent scatters on the roads because on the roads there are cars. Cars move in general, and so the scene changes from one position and the other. But in the middle of the Piazza Plebiscito, which is nowadays not used for parking, we find a lot of persistent scatters because the ground still scatters coherently. Just to let you know, even if it's not directly related to building, also sparsely vegetated areas are good scatters. Okay, no water bodies are not good scatterers. Vegetated areas, so woods and so on, are not good scatterers, but all the rest is a good target. If you need to monitor a precise point, you can put in general what is called artificial corner reflector, which is an instrument that reflects precisely the incoming electromagnetic wave, and you can have a good measurement of that point, of the displacement of that point. I won't go in detail, but what this slide says is that there is a very good correspondence between our persistent scatter interferometry results and other type of measurements such as optical leveling. With experiments we made, we measured the standard deviation of less than 2 millimeters between our measurements and optical leveling, but we can have a lot of measurements. In urbanized areas, we're talking about 100,000 persistent scatter per square kilometer. And consider that the standard scene acquired by the satellite, the actual one depends on the satellite itself, but in general we're talking about 40 by 40 kilometers, an acquisition of 40 by 40 kilometers, so it's a lot of measurements. And for each of these you have the mean velocity and the displacement evolution for urbanized areas or around railways. In grassland areas, of course, this number decreases. The PS monitor, the 3D positioning is instead of metric resolution. So very quickly, also here, we are talking about a technology that can monitor at a large scale very high wide areas. This is the result of a very important project funded by the Ministry of Environment in Italy for the monitoring of the whole Italian territory. On the left, ERS is a type of satellite, of a sensor, and is the earlier results. Then on the right, you can see EMSAT is a follow-up, and at this scale, you can only see the very large phenomena. I don't know if you with a pointer, but you can see around Bologna, that's a well-known subsidence area due to water extraction. And if you look at EMSAT near L'Aquila, that red dot are the consequences of the earthquake. It appears in EMSAT because it was during the EMSAT monitoring. You can move from that scale to a much higher scale. We will see the result later on by choosing particular sites. This project, we are talking about 10 billions of persistent scatters ground deformation measurements on the whole Italian territory that cover almost 20 years. So it's an important tool for people who are interested in security in general. Very quickly, this is what we measured near Rome with ERS, MSAT, and Cosmos Skynet, these three sensors. And you can see that in the same area, you see that the plots are made on the same scale, on the same y-axis. That same area, that same point is getting slower and slower in the course of these 22 years of monitoring. Of course, there is a trade-off between the area you can observe and the number of PS you can detect. This is a Cosmos Skynet very high resolution result near Naples. You can see that each dot is a persistent scatter. There are a lot around along the railway and the highway. If you go for high resolution, but not very high resolution, you have the Sentinel. You have still a lot of measurements. These are free data from the European Space Agency, but for technical reasons, they are fewer and the positioning is not as accurate. But these are two-dimensional measurements. What about three-dimensional? For example, this is the Centro Direzionale in Naples, and you can see that these are very tall buildings, and you can see that the PS gathers along the facade of this building. This is a 3D model, and there is part of the model that is missing, but you can recognize in the center of the Centro Direzionale a surface which is the roof of another building whose model is missing, because the PS align very correctly. And this is the result, for example, with the high resolution, so less resolute sensor. An example of infrastructure. This is the arch bridge in Astana, in Kazakhstan. You can see we can detect a lot of PS on the building, on the arch. And on the top there are some persistent scatters that have relevant velocity, for example. So then it's the job of the structuralists to understand what's happening, but we can measure this. For example, these are 3D positioning. These are power line towers that can be reconstructed by their position. You can see the several PSs on the trellis. And an interesting thing is that even if most of these are green, meaning that there is no strong movement, actually when you go and look at the displacement evolution, you can see that the top of the trellis experience thermal expansion. Okay, so this is something you have to take into account. Of course, if it's green, it doesn't mean that it doesn't move. It means just that the average velocity is near zero. And while at the basis this phenomenon is not present, of course. Another interesting concept about interferometry for infrastructure monitoring is that you can study not only the infrastructure but what's around it. This is a railway along the Black Sea. The railway itself is stable, more or less, but there are very important landslide effects right onto the railway track. So this is another important application, of course. And you can have the evolution, of course. Okay, now this is another example instead of building stability. This is a building in Rome, and first of all, look at the results on the 2D image. You can see that there is mostly green, but it has some red persistent scatter on the bottom and blue one on the left. This means that along the line of sight of the satellite, the building is experiencing that kind of movement that is indicated in the 3D structure. You can see that the two paths are diverging on the two plots on the side, and the plots end around September 2016, because this building collapsed after experiencing all these problems. This is important because do you remember I showed you that at the beginning that there were two valleys with two landslides both downwards, but were seen as one red, the other blue by the satellite because of the angle of incidence. In this case, this building the roof is flat mostly, so this is not that phenomenon. This is actually one side is moving towards the satellite and the other one is going down, and this is the end result. But you don't need to monitor a single building, you can monitor all areas. This is one in Jiangnan district in China, and they experienced a very fast building problem, and they are experiencing a lot of subsidence in several neighborhoods, and even important ones. We are talking, for example, we are talking here about 14 centimeters of displacement, 16 centimeters here. Even a change in the type of construction has an effect. Here is the printing market in Guan. The residential area around the market is stable. The market itself was built with the foundations that were less deep, shallower, and so it's experiencing quite relevant displacements that we didn't know about this one, but then our partners went on site and they saw what's actually meaning. So I am not a structural engineer, sorry, but I think this is relevant. So this is what those red areas mean, okay, in the previous image. There are also other phenomena, more or less relevant, directly impacting on stability. For example, but something you have to take into consideration when you analyze the situation. For example, here is still in China, near the Yellow River. You see that there are some areas that are red. The red here means more than 3 centimeters per year of displacement. And here there is a strong correlation between the water levels of the river and the displacement of the structures. There is a slight delay because it takes some time for water to infiltrate under the building, but this is a strong correlation. Once again, this is London. This is the gas that were detected on London. First of all, you notice that it's almost covered except for the river Thames and for some parks. These are the areas that are not measurable. But you can see these lines, yellow lines. This corresponds to the subway lines that were built in that period. So this is a phenomenon that's happened. The next slide, I would like to introduce you processing a kind of information that can be useful after can be produced after these results by combining the results obtained by two different geometries: ascending geometries when the satellite was from south to north, and ascending one from north to south. If you have two information of the same scene from two different line of sights, you can combine them and measure the vertical movement and then the east to west movement on the ground. This is I chose this one because it's quite peculiar. This is a Campi Flegrei near Naples, which is an area affected by strong volcanic phenomena, and the fact that this is the ground is raising at more than this is 10 millimeters per year. Well-known phenomenon, but very important because there are more than 3 million people in this area. And this is the vertical component. You have imagined this one as a dome that is raising. This means that if you measure the east-west component, you can see that the two sides are going sideways, because if this dome is raising, the two sides are going sideways. This is I put this information here because once again, this is a powerful tool, very powerful tool, but you have to understand what those measurements means, because otherwise it would be a bit tricky. However, these results were confirmed by comparison with the GPS leveling tools. This is from Campi Flegrei once again. And one last general picture is about that red dot that appeared in the MSAT results, the L'Aquila earthquake. This is the aftershock after the earthquake, the deformation of the ground, so you can monitor even this kind of phenomenon. With with the University of Perugia, we collaborated for the Gubbio case study, and I won't go. I suppose that there will be a discussion about this. Our side of the processing was to perform two processings, one in ascending and the other in descending. The time frame were between 2011 and 2017 on the whole area of Gubbio. But then we concentrated, we studied the stability of the Palazzo dei Consoli. We gave the results to our partners and they studied stability. But the point is this one. This is a 3D model of the Palazzo dei Consoli. Onto this model, we projected the persistent scatters that fell on that are pertinent to the Gubbio Palazzo dei Consoli. Here you can see the scale is minus 3 millimeters plus 3 millimeters. So there aren't very strong movements, luckily. Not talking about 30 centimeters per 3 centimeters per year in China, but there are still some movements. For example, at one side of the building, you can observe this displacement of 1 centimeter. It's not a lot, but consider that this is a relative displacement to other points on the same building. So the building is experiencing this different movement in different directions. This is on the other side, for example. You can see some more colored points, which means stronger movements. I'm showing just some evolutions of relevant and interesting points. I will leave to, I think Nicola will speak about the meaning of these displacements and the effects they have on the actual building. But even on the roof, several parts of the roofs are moving in different ways. And one interesting area, you can see that points that are very close to one another, they are moving in different directions. And an interesting result that we found is that, for example, there was, here you can see the movement of 3 persistent scatters on that facade that I showed you before. They move roughly in the same way at the beginning, with the diverging movements during winter, but then recovering during summer. But then in the winter of 2013-2014, what happened is that there were several seismic phenomena, and what we measured was a divergence in the displacement, which was kept for the rest of the measurements. So this is a type of application of our persistent scattering interferometry to cultural heritage in general, to building monitoring. The Heracles case study is the results were shown in part before, but what we have, this is concentrated on the Knossos Palace. You can see that in general the buildings are stable, but there are some points that experience displacement, and this can be interesting to investigate, of course. Here, for example, in this 3D vision of the same results as before, you can see that there is a building with a side that is experiencing a differential movement with respect to the other parts of the building. Is this a danger, a strong danger? This is something only structural engineer can tell us about. We can measure these results from satellite with quite cheap, not so expensive technique. These are other. You can see actually there are several points of the site that are affected by relevant displacement. The site in general is stable, let's say, but some parts must be investigated. Moving to the Cules fortress, of course, even here the fortress is mostly stable, but several parts of the structure are affected by displacement, which in itself is not so strong, but it's strong because it's differential with respect to other parts of the building. And in the long term, this can affect the structure, of course, other structure. So from the Heracles framework, from our work in the Heracles project, we arrived to formulate procedure for the monitoring of structural stability in buildings. Because we realized that using the satellite sound interferometer is very cheap and gives you quite good results, very good results in general, and at a low cost. But then, if you really want to know what's happening, and you have to take really care about the building, you can use an automatic identification of crucialities. For example, the red points that are surrounded by green points, I mean structures that are moving fast around stable points. This is a criticality. And then you have to perform a detailed on-situ analysis of what's happening, because this is very important. Geological, geotechnical, and other instrumentation. And so this is possible to, this is very important, it's possible to compare and calibrate the results you obtain in situ with the results you have from survey. This work was, of course, done within this framework, and we are very happy to have collaborated with our partners. I wanted to say just this. Thank you for that.
Technology is really interesting from an engineering point of view. We have discussed this several times during the course of the project. And the results you have seen about the permanent displacements of the Consoli Palace after the small seismic sequence that affected Gubbio a few years ago, I think is something that demonstrates the very promising characteristics of this technology. So now we have Professor Gabriele Milani from Politecnico di Milano. As I told you in the introduction, the school of the Heracles project is not only a dissemination event of the project, but it's also an occasion to open a discussion with leading experts, also not participating directly to the project, but of course collaborating with us from a scientific point of view, leading experts in the fields of historic structures, in particular masonry structures. So today we have three excellent, outstanding colleagues. First to speak is Professor Milani from Politecnico di Milano, which is quite appropriate in this case. And we talk about fast seismic vulnerability evaluation of towers and churches by means of an adaptive NURBS, linear kinematic FE limit analysis. Thank you again.
Thank you, Professor Ubertini, for the invitation, and thank you all for being here. My presentation, as Professor Ubertini anticipated, deals with the seismic vulnerability of two very important historic masonry buildings that are in particular towers and churches. And the topic is extremely interesting because in this slide, for instance, you see on the left the collapse of one church in Campi di Norcia during the 2016 earthquake, and in the center you see the Finale Emilia clock tower collapse during the seismic sequence occurred in Emilia Romagna in May 2012. And on the right you see an overturning of the facade of a church near Ferrara, again during the earthquake occurred in Emilia Romagna in 2012. But as you can see from the pictures, it is pretty clear that the collapse of such kind of structures, historical structures, is very peculiar. Indeed, for churches you see that the collapse is almost always a collapse that is local. For instance, for Campi di Norcia you see the out-of-plane overturning of the facade that completely destroys the facade of the church, as well as the collapse of the lateral walls. In the case on the right, you see again for the church a complete detachment of the facade from the lateral walls. It is probably an indication that the interlocking between perpendicular walls can play a crucial role in the definition of the vulnerability of such kind of structures. Also, it is strange the collapse of the tower in the center, because one expects roughly that a tower during a seismic event behaves like a cantilever beam. It is not always the case, because in the majority of the cases we see that collapses are characterized by crack patterns that are quite different. In this case, for instance, the collapse is due for the formation of a vertical crack that spreads from the base to the top of the tower. So let's start with the two topics separately, and let's start with churches. So the question is how to evaluate the vulnerability under seismic action and how to implement a seismic upgrading that can make sense. And the reference are the guidelines for the built heritage that date back to 2011, and the recent Italian seismic code and the guidelines for the seismic code of 2000 and of the last year and released this year respectively. So we have some guidelines that are specifically devoted for such kind of structures that are very advanced. Let's see what they say regarding the evaluation of the vulnerability of such kind of structures. Let's say that in general we have at disposal different numerical approaches to deal with the vulnerability problem evaluation of masonry churches that I have summarized into this table that you can see on the slide on the right. Basically, I subdivided these numerical approaches from into 5 different groups, starting from the technique having low complexity and ending with the technique with the highest complexity that you can find with the numerical models. So the first technique is the so-called EFA, so it is an elastic eigenfrequency analysis. It is an analysis that you can do with standard commercial codes because it is elastic and also doesn't need that the user is particularly skilled in the vulnerability evaluation of historical constructions. The second approach is the so-called response spectral analysis, RSA, and we will see later on during the presentation what I am meaning with this acronym. And the third approach that is somewhat more complex is the so-called pushover analysis. It is more complex because the materials are non-linear indeed, because masonry is definitely non-linear under horizontal loads. And the fourth approach is the so-called kinematic limit analysis that can be done with the different approaches, and this is the reason why there are these blue arrows in the slide that refer to different sub-approaches. 4A, for instance, is the kinematic limit analysis with pre-assigned failure mechanism. That is an approach that is recommended by the Italian code for the built heritage, so it has got a very low complexity. And the second one is a kinematic limit analysis with few smart elements, but with a mesh that is subjected to a smart adaptation, and this is the approach that I would like to propose to apply during this presentation. The complexity remains still low, of course is less complex, the level of complexity is higher with respect to the pre-assigned failure mechanism, but it is less complex with respect to the kinematic finite element limit analysis, that is 4B. That is a limit analysis made with the kinematic theorem of limit analysis, but with a finite element discretization. So the discretization is very similar to an elastic discretization, but instead of having materials that are elastic, the materials are rigid, perfectly plastic. And the last approach is the most complex. It is the nonlinear dynamic analysis that you can perform only if you are a skilled user, a very skilled user, and you have got finite element codes that allow you to implement for masonry into the model a material that undergoes damage and plastic dissipation at the same time. plus softening, of course, because meso is a material also that exhibits a lot of softening, especially in tension. So the matter of complexity is not a matter that was invented by me, but comes out from a survey and from the opinion collected of about 100 technicians on the reliability and on the difficulties of the different approaches that I have mentioned above. And as you can see, the results that came out from this survey confirm the level of complexity that I have shown you in the previous slide. So let's start with a summary of the first approach, that is the eigenfrequency analysis. So it is a very simple analysis that you can do, making, for instance, in this case, you see a model that is a complex model that is elastic, made with three-dimensional elements with a commercial code that is subjected to a standard eigenfrequency analysis. Then you find the different eigenmodes and you put the eigenmodes into this diagram on the bottom of the slide with the excited mass. And you superimpose along the horizontal axis where you can find the period of the structure, you superimpose the spectrum. The spectrum in this case is a real one that was observed during the Mirandola earthquake, during the seismic sequence of the Emilia-Romagna earthquake, but as you can see, what it is important to see is that all eigenmodes are local and they excite a very low percentage of mass, but the eigenmodes that excite the highest mass are more or less located in the plateau of the spectrum. This means that they are very dangerous, and then they can be also an indication of the activation, or at least the first activation, of a failure mechanism that resembles to the eigenmode that you can find with the eigenfrequency analysis. So always when you use this eigenfrequency analysis approach, you have to, it is suggestive to further analysis that can be done with the kinematic limit analysis with pre-assigned failure mechanisms that is recommended by the Italian code. The second approach is a standard one, is the so-called response spectrum analysis. It is done again with an elastic finite element discretization of the structure that you can see on the bottom right of the slide. And after the processing phase, you do a standard verification on each macro element. I mean, it can be pier, or a wall, a facade, or a spandrel, if you can find spandrels in Masonry churches. That can be out of plane rocking, in plane flexural behavior, and in plane shear. You normalize these actions that you can find with RSA analysis with the resisting ones, and you find color patches that are normalized against the verification that you are doing. So if you find, for instance, a color patch, as in this case, that exceeds 1, this means that you have some macro elements that are not verified. The ratio between the number 1 and this number that exceeds, the maximum number that exceeds into the color patch the unitary value, provides you the vulnerability of the structure. In this case, what you have to do is a recursive approach, so you have to reduce homothetically the spectrum that you used for the response spectrum analysis until you find all the diagrams with color patches that do not exceed the unitary value for the verification of each macro element. So this one, for instance, is a slide that reports you what happens reducing for the three different verifications that you have to perform on a church, the results reducing the spectrum. You can see, for instance, that this church has difficulties for the overturning of the facade that exceeds the capacity the out-of-plane resistance of the macro element called the facade. It is finite element model. It is a model that can be done also by a practitioner, so it's something that can be done in common design and in common verification. Pushover analysis is something that can be considered more difficult to perform, but the guidelines for the build heritage allow you also to simplify the model that you can use, the nonlinear model that you can use for measuring, and it is allowed also to use also materials that are elastic, perfectly plastic, with isotropic behavior. So you can use, for instance, materials that behave like a more Coulomb material with perfect plasticity, also with non-associated fluoride. It is something that several finite element codes that you can find in the market have already implemented, and therefore you can perform pushover analysis according to the guidelines for the build heritage. The advantage is that in this case, applying G1 and G2 distribution according to the Italian code, then you can find, as you can see in the deformed shapes at collapse of these churches, you can find that the failure mechanisms that are active are, in the majority of the cases, partial, and they give you, the approach gives you an estimation that is reliable in this case, because the material used is nonlinear, on the activation of partial failure mechanisms, so an indication of the weakest parts of the structure that need to be strengthened in order to reduce the vulnerability. The disadvantage is that there is a discussion on the measuring quality that you have to use, and also the level of interlocking between perpendicular walls is a matter that is only a practitioner that can decide after a proper survey, case by case, during direct investigation, on-site investigation. The fourth approach is the kinematic limit analysis. The kinematic limit analysis is based on the theorem, on the classic theorem, kinematic theorem of limit analysis. It bases indeed on the principle of virtual works. It is also called a linear kinematic analysis, and you have basically to decide, according to the Italian code, a failure mechanism that is active. For instance, the overturning of a facade, as in the case of the church that collapsed during the Emilia-Romagna earthquake, and that I showed you some slides ago. And you have to decide the position of the loads that are acting on this macro block. The vertical loads are typically gravity loads, or loads coming from some floors or roofs that are in connection with the macro block forming the failure mechanism, and the direct and indirect seismic loads that are applied to the structure statically. So you write the power better than work, even if the Italian code speaks about work, that is expanded by the forces that depend on the load multiplier, so the forces that depend on the seismic load. This alpha zero is the ratio between the acceleration at collapse, horizontal acceleration at collapse due to the application of the seismic load, and the gravity acceleration. These are the unitary forces multiplied by the displacement that are in the formula. In the first formula you see here okay, in any case this one are the forces that depend on the load multiplier. This one is the load multiplier that depends on the seismic load. This one are the stabilizing forces that are basically the gravity loads. And this one is the internal dissipation that, according to the Italian code, is set to zero because the material is unable to withstand tensile stresses. So, the Italian code also helps you because it gives you the possibility to limit the calculation on 28 different pre-assigned failure mechanisms. For instance, here I have shown failure mechanisms, out-of-plane mechanisms involving the facade. There are also other mechanisms that involve the triumphal arch, the apse, the lateral walls. In this case, this one involve the lateral wall, both the lateral walls and the central barrel vault. And therefore you can find the minimum of the failure multiplier that is associated with the first activation of the failure of the church. But what you can do is also to discretize the entire structure into finite elements and to use the same principle, so the same theorem, kinematic theorem of limit analysis. The problem is that the problem that comes out is a minimization problem that is constrained. This one is called in mathematical programming a linear programming problem. It is a problem that is not implemented directly in the most diffuse commercial codes, therefore it is difficult to be used by practitioners. And this is the reason why it was considered by practitioners after the survey very difficult to use. But here I have, for instance, some results that I found with a code that is a non-commercial one that I implemented by myself. As you can see, the mesh is exactly the same as the mesh that you can use in linear analysis, but takes into account the linearity of the material and provides immediately the active failure mechanism that in the majority of the case is always partial and involves out-of-plane loaded walls, and the collapse multiplier that provides indirectly the acceleration, the seismic acceleration and collapse. The last approach is nonlinear dynamic analysis. In nonlinear dynamic analysis you have to apply an accelerogram that can be real or spectrum compatible. In this case is linear, is real, sorry. And the material is a material with softening in both tension and compression, as you can see, and exhibits also damage but also plasticity. So it is very complex, but it is something that is very suited for masonry because masonry has got all these specific features, unfortunately. Here I would like to show you some videos of the nonlinear dynamic analysis that we performed for two churches. As you can see, it is quite clear again the formation of partial failure mechanisms on the facade, the collapse of the upper part of the bell tower, the damage evolution of the apse and so on. And also you can plot other very interesting numerical data such as the kinetic energy, the damage that is cumulated, and the horizontal displacement of some control nodes that are very important to check what's happening during the application of the accelerogram. The approach that I developed with my research group recently is an approach that is strictly related to the Italian code but supersedes the limitations of the Italian code. The limitation of the Italian code is that you use always pre-assigned failure mechanisms. With this approach, you use a very coarse mesh, so you don't have all the drawbacks that you can have with analysis calculation, but this coarse mesh is adapted with an algorithm that the user doesn't see at all in order to find the exact failure mechanism of a facade during the application of a seismic load. In this case, the user then meshes the structure in a very simple way with very few finite elements and finds immediately the correct collapse load and the correct horizontal acceleration at collapse. Here you can find some results that we found in a church, for instance, with the application of a transversal acceleration. You can see the correct evaluation of the out-of-plane overturning of the lateral wall, and the overturning of the facade with the correct interlocking with perpendicular walls, also checked with what happened directly in situ after in situ investigations, and also the out-of-plane overturning of the apse. So let's go very quickly to speak about towers, because I have only 8 minutes missing. The references again, the guidelines for the built heritage. Just to be very, very quick, what it is important to analyze for a masonry tower is the so-called acceleration factor. It's a ratio between the acceleration at collapse that you find for the tower and the acceleration that is required in that site by the Italian code. The Italian code suggests to simplify the problem to a cantilever beam. But what we found, both after surveys, in-situ inspections, and after sophisticated numerical analysis like pushover and nonlinear dynamic analysis with concrete damage plasticity, approaches is that the crack patterns at collapse are very, very, very different by the crack patterns that you can find using a cantilever beam. In the majority of the cases, the cantilever beam collapses for the formation of a flexural hinge. That is not exactly the case of this tower, of course. So, another demonstration of the fact that the approach by the Italian code is not so reliable in the majority of the cases is this slide. In this slide you can see here a comparison between the acting bending moment and the resisting bending moment according to the Italian code for 2 different towers. You can see that the problems that you can find are always located at the base with the formation of a flexural hinge. But nonlinear dynamic analysis with the distinct element method and nonlinear dynamic analysis with concrete damage plasticity approaches and 3D discretizations show that the behavior is totally different, with the formation of cracks that spread on the upper part along the vertical lines. So what we thought was that it was better to follow the idea suggested by the Italian code for the churches. So to try to investigate different possible failure mechanisms and use the kinematic theorem of the limit analysis. Of course, with these different simplified mechanisms that take into account the numerical results that we found previously, you can repeat very large Monte Carlo simulations changing the tower slenderness and the resisting shear area in order to find what is, in the different case, the failure mechanism that is active. In this case, the different colors indicate the different failure mechanism active. So you can see, for instance, that for a tower that has got a normal slenderness like 5, the most probable failure mechanism is the formation of a crack pattern, of a vertical crack pattern. So it is very different with respect to the formation of a horizontal hinge. Of course, you can also take into consideration that masonry is not exactly an tension material, but can resist a little bit to tensile stresses. With different strength domain, then you can find different results in agreement with the mechanical properties that you found, that you input at the beginning for the masonry material. So you can see, for instance, that in this case too, when you have a very low cohesion and very low tensile strength, then you have a region where you can have also, you can experience also sliding near the base. This is very useful for a strengthening intervention, because a strengthening intervention is effective if and only if you are able to identify the correct failure mechanism. If the failure mechanism is this one, then the application of horizontal tie rods is effective. But if the failure mechanism active is this one, so the overturning at the base, the application of horizontal tie rods is totally ineffective. So you can see here, for the case 1 that we discussed previously, what happens in absence of horizontal reinforcement and in presence of horizontal reinforcement. What you can observe is something that is pretty trivial. So if you apply horizontal tie rods, the the yellow collapse that is associated to the formation of the vertical crack is improbable in case of this kind of reinforcement. Conversely, if you apply vertical reinforcement, then the vertical reinforcement is much more effective for the second failure mechanism. It is also effective for this so-called Hyman crack pattern with this inclined flexural hinge, is the purple one. It is effective also for the third one. And indeed, you can see that for the green one is slightly effective, for the yellow not at all, and for the purple it is quite effective, for the blue is much more effective. So just to develop further the approach, the simplified approach that we thought, thinking about the approach used by the Italian guidelines for churches, we decided to sophisticate a little bit this failure mechanism using a NURBS volumetric discretization. So with this failure mechanism that are characterized by different cutting planes on a geometry that is made with NURBS, and with the position and the shape, the slope of these cutting planes that is automatically adapted in order to minimize failure mechanism by failure mechanism the collapse acceleration, according to the in agreement with the kinematic theorem of unit analysis. And we applied to this method to two different case studies. This one is the bell tower of the cathedral, of the Ferrara Cathedral, city center of Ferrara, very important bell tower. We performed pushover analysis with Abacus to see what was the failure mechanism active. It's a sort of Hyman failure mechanism, as you can see from the picture. And we performed also nonlinear dynamic analysis. Here you can see the video of what's happening with the application of an accelerogram that was registered in Uganda during the 2012 earthquake, and there is a good agreement, as you can see, with the results that we found with pushover analysis. The same is found also for the NURBS adaptive kinematic unit analysis that finds that the lowest acceleration at collapse is given by this mechanism. It is very similar to the mechanism that we found, this one, that we found with sophisticated nonlinear dynamic analysis. The same for the last example. This one is the bell tower of the Pomposa Abbey. Pushover analysis. In this case, we have an irregularity along the 8 with the thickness that suddenly changes in the middle, starting from here to the top of the tower, and this is responsible for an overturning with again an Hyman failure. Sorry, but time is over. I have only 2 slides to show you. So with the activation of a failure mechanism with an inclined real line, and again nonlinear dynamic analysis that confirm that failure is again due to the formation of a hinge, of a inclined flexural hinge in the top, near the top of the tower, because of this irregularity on the thickness of the perimeter walls. The same is found with the NURBS simplified kinematic unit analysis. I would like to underline that this approach needs only a CAD or a rhinoceros discretization with NURBS of the tower, or in the previous case of the church. If you use the simplified approach without taking into account the special geometry of the tower that you have to consider, then you can, as in this case, because of the irregularity of the perimeter walls, you can commit some errors also in the identification of the active failure mechanism. That's all, and thank you for your attention.
for your very interesting presentation. I would suggest that we postpone a little bit the break, but not too much. So we will have the next speaker now, that is Professor Clementi from Università Politecnica delle Marche, and with the agreement of our upcoming speaker, we will postpone the talk of Professor Formisano to the post-break phase. Professor Clementi will talk about the non-smooth contact dynamics method for the analysis of mesoring structures.
Good afternoon. Thank you for the kind invitation. Thank you, Filippo. In this slide, in this presentation, I want to highlight the main feature of the non-smooth contact dynamics method applied for the seismic assessment of cultural heritage. In particular, I want to highlight what is the idea at the base of this quite new method. In this slide, you can see the 5 main points that I hit during my presentation. It's quite well known that our nation has an intense seismic activity, in particular in the last 25 years, 5 big earthquake strokes all the nation. We remember the first one of Marche, Umbria, the Molise earthquake, then L'Aquila earthquake, another one in 2012 of Emilia-Romagna, and the last one of the Central Italy earthquake that strokes a lot of little villages along the Apennine zone, like the village of Amatrice, Arquata del Tronto, Visso, Norcia, Bacuzzo, Camerino. The main problem is that the seismic action give a lot of damages inside to cultural heritage, in particular to churches or towers. In this presentation, I want to analyze the seismic effect of over some particular churches, in particular the Apennine churches that are a little churches along the Apennine zone. Okay. I have analyzed these 5 churches inside the city of Montefortino, Sarnano, Ussita, Camerino and Fiuminata. With this new method, namely the non-smooth contact dynamics method, first of all I want to say something on the historical from historical point of view of this case study. The first church is the Church of San Francesco in Montefortino. Is a Romanesque Gothic church. During the Umbria Marche earthquake, it suffered a lot of damages, and after some retrofitting intervention, it was again damaged during the Central Italy seismic sequence, where a lot of damages was observed along the Triumphal Arch, on the main facade, and on the connection between the tower and the nave and the wall of the nave. The second case study is San Francesco in Sarnano, another little churches with only one little nave. This church was damaged during the Umbria Marche earthquake. Some retrofitting intervention was added to these churches, and again with the last Central Italy earthquake, some damages appears in the Triumphal Arch and in the main facade. Another case study is Sant'Anna in Camerino, another little churches along the Apennine zone. Also, this church has a lot of damages during the Umbria Marche earthquake, and again with the last Central Italy earthquake, a lot of damages were observed in the main facade, where a clear overturning mechanism are observable, and again some damages also in the south facade. The most damaged church is Sant'Antonio in Ussita. It's very near the epicenter of 26 October. This is a very little church in an hamlet of Ussita. It has a unique nave and a little annex near the church, and here you can observe the main damages of the church after the seismic sequence, where a lot of damages appear in the main facade, a collapse of the roof, because a collapse is observable in the bell gable, and a lot of damages also are observable in the wall of the nave. The last case study is the Valcora in Fiuminata. This is quite far from the epicenter, but also in this case we have observed some damages in the annex, but also in the bell gable. And in order to have a clear picture of the potentiality of this method, I present also another case study that is the symbol of the damage and of the destruction of this strong earthquake, namely the Cyclop Tower of Amatrice. This is a work in cooperation with Professor Gabriele Milani. It's quite well known what happens to this tower. This is actually an isolated tower, but it born as a belfry of a church of Santa Lucia that was demolished and was added to the tower a little annex where it appears the staircase. During the Alta Valnerina earthquake, a lot of damages were observed inside this tower, and in 1985 the original bell was replaced by a later one in order to avoid the oscillation of the tower. In this picture you can observe the accumulation of the damage in this tower, starting from the 24th August and until the 18th January. And the main observation are that the damage appears in the bell cell and in the wall of the annex, and these damages is accumulated in these two parts. The tower has a height of 25 meters with a quite good regular blocks that compose the texture of the walls, but a not good measure is observable in the wall of the annex. Here you can observe this not so good measuring. Another important observation is that there is not a very good connection between the tower and the annex. What is the no-smooth contact dynamics method? It is a method that belongs to the family of discrete element method, but it differs from the classical distinct element at least for three main aspects. It does not take into account for any structural damping. It uses an implicit integration scheme and it integrates directly the no-smooth contact law. The main hypothesis at the base of the model is that the bodies are rigid. In this work, I have used the no-smooth contact dynamics method implemented in the LMCC90 software. And in order to have a simple idea on the dynamics at the time of collision between this rigid body, we can consider two rigid bodies, PD and PJ. Pi and PJ are two possible points of contact, respectively on the body B and BJ. It's important to define a local system in order to have a clear picture of the instant of collision between these two rigid bodies. In particular, it's important to define a normal vector and a tangential vector. With G, we define the distance between this point, and with U dot n and U dot t, the normal and the tangential velocity, and with Rn and Rt, the normal and tangential reactive force. Because this method is non-smooth, we must use non-smooth law. The non-smooth law in the normal direction is the classical Signorini law of impenetrability, and here you can observe the clear non-smooth law. That is, you have a reaction if the body are in contact, otherwise you have a reaction. And in the transversal direction, we use the Coulomb's law that is defined with the main parameters, namely the friction coefficient μ. And here you can observe the no-smooth law that is defined with this friction coefficient. The equation of motion has this form where M is the mass matrix, Q is the vector of system kinematical parameters, R is the vector of reaction, and F is the vector of external and internal forces. Since the contact law are non-smooth, reaction and velocity are discontinuous function of time, and again it's important to stress the fact that at the instant of velocity discontinuity, the acceleration are not defined. For this reason, we should use this time step of integration. Here you can observe the numerical model of the Apennine churches, and here you can see the main model of the city clock tower of Amatrice. All these models are composed of rigid blocks that could impact each other or sliding each other. Some numerical results, because this method is based on the definition of a friction coefficient. We have used in the elevation a friction coefficient equal to 0.5 for all the churches, and a value between 0.3 and 0.5 for the civic clock tower. Because we are not interested in the interaction between the blocks and the foundation, we have used a very high value of this friction coefficient equal to 0.9. Because all of the Apennine churches considered in this work are located in different areas where are not possible to have a clear registration of the real acceleration of this seismic sequence, we have used in all the numerical simulation the main shock of the long seismic sequence. Here you can see the main acceleration in the three main directions, x, y, and z, for the three main shock of this seismic sequence. The first numerical results are those for San Francesco in Montefortino. Here you can observe a clear picture of the possible damage after the seismic events. In particular, here you can observe a clear collapse of the dome of the bed. And a lot of damages are observable in the little annex or again in the wall of the a more clear picture of the damage observable after this seismic sequence. It's possible to see here for the Sant'Antonio in Ussita, where a clear collapse of the bell gable of the churches, of the little church, and of some part of the annex or on the rose window of the churches are observable. Another simulation of Sant'Anna in Camerino. Again, the most vulnerable part are the main facade, the bell gable, but also the triumphal arch, with the main shock where the most evident damage inside the church. And here in this picture you can observe the clear activation of the overturning mechanism of the main facade. Okay, for San Francesco in Sarnano we can observe the similar damage that are similar to the real one, in particular increasing the intensity of the main shock. Obviously we increase the observed damage. In particular, here you can see a collapse in the rose window, a collapse inside the wall of the annex, and some clear damage in the last one is church is Madonna of Valcore Illuminata, where it's possible to observe a clear collapse of the main wall of the apse and a clear collapse of the bell gable near the apse. The last numerical results are this of the sea clock tower of Amatrice. You have a clear idea of the real damage observed after the seismic sequence, and here you can observe upwarding of the friction coefficient of the masonry. What we can observed from a numerical point of view. The bell cell is the most vulnerable part of the tower, and this is the most damaged part of the sea tower. And again, we can observe a clear damage inside the the little annex of the civic tower. Okay, with this method it's possible to have a clear picture of different dynamical phenomena of masonry structure, and in particular it's possible to have a very quite good model if we use a very detailed discretization of the masonry. This is one of the main point of this method. In particular, our idea is to have a very clear numerical model of these cultural heritage structures, but the problem is that increasing the number of rigid blocks increase the time of computation. These analyses are very long. In particular, for a matrice, we have used, I think, 1 month of simulation to have these results, but actually we have used a GPU in order to have a more quick or fast numerical results, and here you can observe new numerical results in a little masonry towers, that is the civic tower of Rotella near Ascoli Piceno, and here we have used a very detailed geometry. In particular, we have modeled the internal and the external leaf, and inside we have used a very big number of cubic blocks in order to have very similar to the reality in order to have a clear composition of the masonry. But again, this simulation is very time consuming, and I hope that in May we have the final results with the accumulation of the damage of the 3 main shocks. Okay,
Francesco. This presentation was stimulating a lot of debate with colleagues here, and one question, I know we don't have time, but just to know if this software is an open source.
It's an open source, the solver is an open source. We have a pre-processor and a post-processor in order to have a better discretization of the geometry and a better visualization of the main results of this method.
Thank you very much, very interesting. So as anticipated, I would suggest that we make now the break. Session of day 1, and the speaker is Professor Formisano from University of Naples, Federico II, that will talk again about analysis of the behavior of masonry structures, and in particular seismic vulnerability of masonry building aggregates and risk analysis of historical centers.
Good afternoon to everyone. First of all, I would like to thank Professor Bertini and his team for this kind of invitation to speak about the seismic vulnerability of a historical center and masonry aggregates. I can say you that the problem is very complex, since you know that in historical center there are a lot of clustered buildings that are not isolated, but they are in connection to each other. And they generally have been built without anti-seismic prescriptions, with no urban planning, And during the several decades, there were some addition, manipulation, modification to their apparatus. In particular, we can say that these masonry buildings have different number of stories, staggered floors, different history aids, and structural types. So it is difficult to understand which is the real behavior of single structural units when they are inserted in compound. And all the design processes that we have also in our code dealing with the behavior of a single isolated building. So we have two open issues in this case. First of all, how to perform large-scale seismic risk and vulnerability analysis of single structural units, but taking into account their grouping in the compound. And the second question is how to model in detail structural units without collecting information on the real masonry compound in order to evaluate the real safety check of these buildings. So I will try to give you some replies to these two questions. In the first case, I will show you an application in Senerchia, that is a district of a municipality in the district of Avellino in Italy, where I will perform some vulnerability analysis, large-scale vulnerability analysis, taking into account local site effects. In the second case, we made a simplified design approach of single structural units, but taking into account the condition of aggregate. So in the first case, I will show you some information about Senerchia, that is a small municipality in the district of Avellino with about 1,000 inhabitants. And more or less we can say three different expansion processes during the several decades of this small municipality, and that is built around the Monte Croce, around high fortifications. The municipality is characterized by building aggregates that are very similar to the typical built-up that we have in the Campania region of Italy. In the Campania region of Italy, we have the micro-zonation that divides the whole territory in three different areas: high, medium, and low. Senerchia is a part of the second zone, the medium-high seismicity, with the medium-high seismicity, and with an expected peak ground acceleration between 0.15 G and 0.25 G. So this is the territory, of Senerchia, and according to the Reduced Research Project, it was studied within the TACTIS approach, coordinated by Professor Giulio, where the mechanical and typological characterization of the built-up was made. In particular, we defined two different sectors, C01 and C02. C01 was the ancient nucleus of the city that was affected by 1980 earthquake in Irpinia, and now it is not in use. And the second zone, sector C02, is the new zone, the new residential zone that is occupied by the inhabitants of the municipality. So the attention is devoted, in this case, in our study, to the sector C01 in order to evaluate if there are some potentialities of the sector to be restored and to be requalified in the future. In this sector, we distinguish two different types of structural typologies: measured with the timber floor and measured with the steel floors. And we collect some information on the different masonry compounds that are made of more or less 43 structural units. How to perform this? In the recent years, we developed a survey form based on the original form developed by the National Group of Defense Against Earthquake and before by Benedetto and Petrini in 1984, that is based on the evaluation of some geometrical mechanical information of the apparatus of the structures. And in this form, we added 5 additional parameters taking into account the aggregate effect. In particular, the score and the weight have been assigned to this parameter on the basis of a wide numerical analysis we performed. And the class score are varying from A, which is the best class, that is the less vulnerability, to B, that is the worst class, the highest vulnerability. The weight represents more or less importance of the parameter that we have in the form. So we can define the vulnerability index as the sum of the score multiplied by the respective weight, and this index can be normalized into a scale 0-100 in order to have a more direct comparison and also to apply the methodology developed by the RISC-2 project in the framework of the European Macroseismic Scale 98. I would like to show you some brief news about the new parameters we added to the form. In particular, the first is the iteration in elevation that we have among the buildings. This is the best case is when we have no difference in terms of 8. And the worst is class D when the building is between two taller buildings. After, another parameter is the position of the building in the aggregate. The basic case is the isolated case, the class D. In the other case, when we have intermediate position or corner or hidden position, in general we have a reduction of the seismic vulnerability, since in this case it is beneficial the influence of the aggregate condition on the behavior of single buildings. About the number of staggered floors, we have the best cases when we have not staggered floors, and the worst case is when we have 4 floors that are staggered to each other. The 14 parameters is the difference among structural units in terms of structural topologies or heterogeneity of constructive systems. The best system is when a measured building is close to a reinforced concrete one, and the worst condition is when the measured building is close to a building made of masonry but with better quality. And finally, we have the percentage differences in terms of opening area among the different buildings. The best case is when we have no difference in terms of opening area. The worst case is when the adjacent buildings have opening areas larger than the one of the building under consideration. So, starting from this consideration, we evaluated for each of the 43 structural units a vulnerability index that was transformed in the normalized range 0-100. And according to the study developed in the RISC-2 project, we were able to evaluate the damage that should be expected for this building as a function of the vulnerability index and by making variable the seismic intensity. The seismic intensity is defined on the basis of the magnitude as we will see in the next slide. In this case, we can evaluate 5 different types of damage, starting from 1 to 5. 1 corresponds to slight damage, 2 to moderate, 3 to substantial, 4 to very heavy, and 5 to collapse. And so for each building or each structural typology, we can collect the average vulnerability curve, the red one, and also the other curves considering the coefficient of variation that we have in the distribution of vulnerability index or the for the buildings of that for that class, for the given class. So in order to evaluate how, starting from the magnitude, how is changing the seismic intensity, we can use some attenuation laws. In this study, we used the law developed by Crespellani et al. And in order to evaluate the seismic damage scenario, we consider 3 different magnitudes, 4, 5, and 6, and 4 different epicentral distance, from 5 km to 20 kilometers. About the historical earthquake, we consider we had an earthquake in 1985 with the magnitude 4, 1982 with the magnitude 5, and 1990 with the magnitude of 6. So, starting from 3 different magnitudes with different distances, according to the seismic attenuation law before illustrated, we had the seismic intensity to be considered in the relationship developed by Lagomarsino and Giovinazzi in order to evaluate the probable damage expected under earthquake. And this is the results, and we see that for the different magnitude, different epicentral distance, we evaluated that for magnitude equal to 4, starting from 10 km, we have not more damage, we have only slight damage. And for magnitude equal to 6, up to 10 km, more or less, all the built-up should collapse under earthquake. And after starting from 15 km, we have a reduction, a progressive reduction of the damage. Also, in the intermediate case, in magnitude equal to 5, we see that in the first case, at 5 km, we have a lot of damage. But this damage is progressively reduced when the distance increases. At the end, when we have a distance of 20 kilometers, we have only slight damage and moderate damage. But in this case, we did not consider the local side effect, the geographical condition of the site. And so we take a profit of some experimental tests, for example, download or Mars tests that were performed in the site. And so we were able to classify the seismic territory in 3 distinct areas, A, B, and C, according to the seismic resolution of our code. According to this, we evaluated the seismic behavior of aggregate, a major aggregate, which is a typical of the build-up of Seneca, and considering the 2 analysis directions, we performed on these different analyses in terms of seismic risk coefficient for the 5 different types of soils we have in our code and the 4 different topographic categories we have. So, for both directions, we evaluated the seismic risk factor, that was the ratio between the demand acceleration and the capacity 1. And starting from this, by making the ratio between the values of seismic risk factor related to the different categories and category of soil and category topographic category with respect to the basic condition, in this case the A category that corresponds to bedrock, we evaluate some seismic amplification factor that was called FPG. In this case, we evaluated how the seismic effect should be amplified by taking into account the different types of soils and different topographic categories. And we evaluate that this factor is variable from 126 to 196 in the case under study for the soil category. And this was very useful in order to evaluate the difference in terms of damage between the single condition where local side effects are not considered and the one where the damage is amplified. And we see that in the last line, the last row, we see the differences, the increase of damage that we have. That for magnitude 4, we have only a small increase of damage, only 5%. For magnitude equal to 5, we have 50%. And for magnitude 6, we have no damage. That is, in this case, is not sensible, the problem. But if we pass from 5 kilometers of epicentral distance to 10 kilometers, we have that for magnitude equal to 6, we have an increase of damage. So the situation is different with respect to before. And in this case, we have a reduction of the increase of damage. 5 before and now 2%, and before is 50 and now is 42%. If we go on, we have that the trend is always the same. We have a reduction of the damage for magnitude equal to 4 equal to 5, and increase of damage up to about 50% for magnitude equal to 6. And finally, for t equal to 20 km, more or less, we have the same increase of damage for the maximum magnitude, and in the other case, we have always a reduction of the damage. This was very important in order to evaluate the damage distribution, where we can see more or less the same results that we obtain without considering the local side effect. That is, for magnitude equal to 4, we have at 10 kilometers more or less the same damages. That is only slight damages. For magnitude equal to 6, we should pass at 15 kilometers in order to have a more variable distribution of damage. And finally, for the intermediate magnitude equal to 5, we have a very variable ranges of damage that we obtain depending on the distance, epicenter distance we consider. So in this case, we can say that the intermediate case is the one that should be taken into account with more attention. Finally, we evaluate also something about the possible damage that could be subjected intermediate unit and heating unit within a given masonry aggregate in terms of fragility curve. How to perform the analysis, how to obtain the pushover curve in this case? We evaluate for each analysis direction the contribution of the walls, but we should take into account also the contribution of the walls and of the floor of the adjacent buildings. In this case, we reconstruct the pushover curve, and this is in terms of basic shear. In terms of displacement, we make at the top level the average values of the displacement of the different points of the structure. And in this way, we evaluate for the two buildings in two different positions the real behavior in terms of pushover curve for intermediate unit and big unit. Starting from this, according to an empirical approach given by the square project, we can plot the fragility curves according to damage levels defined in Ropier-Magosine scale. We have the probability of damage on the vertical axis and the spectral displacement on the horizontal one. And in particular, we can see that if for a given spectral displacement, in the two cases where that the heat structural units suffer much more damage than the intermediate one due to the torsional effect that we have during seismic action. So I would like to pass briefly to the second topic, that is structural analysis on the structural analysis and simplified design rules on structural units in masonry aggregates. And we see that in historical center we have the continuity and the interconnection among the structural units. And in general, structural units is modeled as a loan. And this is not real, this is not true for seismic application, this does not provide good results, of course. In particular, we would like to know if the aggregate effect is beneficial or not in terms of seismic behavior of the unit. It should be important to model a single structural units at the same time by taking into account the incidence of adjacent structural unit. Since we would like to know the real behavior of a given structure, we should model all the whole aggregate, and this is time consuming since you should acquire a lot of information. So we propose the simplified numerical approach based on the equivalent frame method. It is a technique that is, as you know, usually adopted for framed buildings. So, in this case, we modeled the masonry walls according to the first study developed by Vangelis and Calvi as an equivalent frame represented by a linear element which represent the piers and the spandrel, and the rigid part is joint panels that are not subject to strong damages in case of earthquake. In this case, these frame elements are considered as a linear component with the lumped plasticity model. The equivalent frame can be adopted into general programs, and the most common type of masonry aggregate that we know is the so-called row housing building that is composed by a series of structural units that are arranged according to the existing streets. An example is the Sallegio complex in Caserta, but also in other cities of Italy. And the case study is this one. We used three distant structural units of the same dimension that are based on a residential use. Each single structural unit has 11 by 15 meters. It develops on 2 stories. It was made by Napolitan yellow tuff stones with the floors made by timber beams and planks. The frame model was built up by means of the SAP 2000 program, and we performed 2 different analyses. One on the wall aggregate. We consider also equivalent bracing in order to evaluate the real stiffness of the frame of the floor. And the second model of the single isolated building that can be take off from the central position or from the head position of the aggregate. In this case, with this simplified approach, we can evaluate by extrapolating this unit from the whole compound, which is the real behavior of the structure. And after we would like to model only this structural unit by putting some elements in order to reproduce the boundary condition. These elements was based on the nonlinear elastoclassic links, as we will see in the next slide. This is the whole aggregate, and this was the two structural units taken off from the model, the intermediate unit and the unit. We made a pushover analysis according to the two loading distributions based on our code. This was the pushover curve of the whole aggregate, and we considered also the distribution of classic hinges that were developed almost at the base of the piers. And we have evaluated, we have two directions of analysis. The first is the x direction, longitudinal one, and the second is the transverse y. In the longitudinal direction, if we compare the behavior of the whole aggregate with the behavior of the single building isolated, and the other two buildings taken off from the aggregate, we see that we have not great difference. So in this case, we can model in longitudinal direction the building as alone, without boundary condition. Instead, if we evaluate the behavior of the three same units, we see that some differences in terms of both strength and stiffness are noticed. So in these cases, if we would like to study the single buildings, in order to take into account the aggregate effect, we should put some nonlinear elastoclassic links in order to create some appropriate boundary conditions. How to assign this? For intermediate building, we have to put on both sides of the piles the point corresponding to the upper joints at the two levels. Instead, in case of single buildings, since one side is free, we have to put this only on one side, the one attached to the other structural units. And now, how to assign the load, an appropriate load to these nonlinear elastoclassic links. In general, we make an inverse passage, so we have evaluated which should be the values to be assigned in terms of strength and stiffness to these values according to the results of the analysis on the whole aggregate by taking off the structural units. But once we obtain this value, we propose two different relationships, a simple relationship, in order to evaluate how to assign, only on the basis of few information whole compound, the characteristics in terms of strength and stiffness of these links. And these are the two relationships, are based on a few geometrical information. H is the story 80 meters, L is overall length of the compound minus the unit under investigation, T is the transverse direction of the compound, alpha and beta are some coefficient taking into account the position of the building and also the material mechanical properties. So we made a calibration process and we evaluated the values of alpha and beta to be used to have a good agreement of results with respect to the case of the whole compound. This was the coefficient for the intermediate unit, this was for the heat unit, and at the end we evaluated that for both cases, in the dashed line we have the real behavior, and with the continuous line we have the pushover curve obtained on the basis of the simplified relationship. So in this case we have a good agreement of results, even if some future development of the study should foresee the application of this procedure to a lot of series of aggregates into the different historical centers of Italy, especially in order to evaluate the effectiveness of the relationship that we provided, as well as the coefficient, the values to be provided to the coefficient alpha and beta in order to have also simple relationship to foresee the real behavior of the single structural units in aggregate. Thank you for your attention.
For a very nice presentation. As you see, masonry is a very complicated material that whose modeling is still challenging, and several approaches are being developed in the literature to deal with this kind of problems. So now there is a series of presentations from the research group of University of Perugia. We will start with myself, talking a little bit about some results we have been achieving within Heracles in monitoring activities. So I jump to the next. Yeah, that's one for the presentation. Yeah, this is a presentation that summarizes a little bit of the activities we have been doing in Heracles. Actually, it will not cover all the topics because there will be other presentations on the same topic also tomorrow, as I will mention during my presentation. So here is a brief outline of what I would like to discuss. So first, I will introduce a little bit of theory and one example on anomalies detection in long-term SHM, so what's typically called damage detection in the literature, because this explains what we are doing essentially in Gubbio. Then I will talk about Gubbio, and in particular you have seen that in Gubbio the project has focused on the Consoli Palace and on the masonry walls of the town. So I will show you results, some results relating to monitoring activities in both these case studies and then conclusions. Alright, so in structural health monitoring there are 4 questions that should be answered. The first question is the most important one. The question is the structure damaged or not? So this is called typically the damage detection task. So to define, the challenge here is to define an algorithm that from data recorded on the structure can answer automatically this question: is there a damage or not? The second question is where is the damage? This is kind of an important question. I will not talk about this. My talk is only on stage 1, but there will be a couple of talks later that will address from different perspectives the second stage. The third stage is what is the extent of the damage, and the fourth is what is the remaining service life of the structure. Well, it's our opinion that in a structural engineering, civil engineering perspective, stage 1 is very important, stage 2 is important, the remaining 2 stages are less relevant, because actually what we want to develop is something low cost that tells us there is a problem, go in the field and check what is the problem. If we can say where is the problem, we will save time. For example, after an earthquake, we need to intervene on the structure and install safety provisions to prevent collapses during aftershocks. So we need to know when to intervene in the structure and where to intervene. Actually, what's the extent of the damage? This is a question that hardly could be solved. Actually, even stage 1 and stage 2 are quite challenging. So it's our opinion that stage 3 and stage 4 are really, really, really difficult, but less relevant. So I'm only talking about stage 1. Is the structure damaged or not? There are several approaches to deal with this problem, and we have to say that sometimes damage is not observable. So we have to be fair in saying that when we do monitoring, there could be collapse mechanisms that cannot be observed before and cannot be anticipated. We need to know this. It's not always the case that we can detect the damage on the structure, but sometimes we can. The different approaches available typically follow more or less this structure. There is, especially if we talk about long-term SHM, so continuous SHM, there are 2 possible approaches. One is to observe continuously the structure and acquire data in a continuous fashion. The other approach is to acquire data only when there is an event. So let's say I acquire data continuously, but I save the data and analyze the data only if there is an event, like an earthquake. If we talk about continuous SHM, the approaches more or less follow this line. There is an operational evaluation, which means that the structure is observed in its operational condition, normal condition. So if it's a bridge, when the bridge is open to traffic, it's doing its normal job. Then this data, that can be static data, can be displacements, can be rotations, can be whatever. In our case, these are accelerations. Then this data is typically processed, so it's elaborated. The data processing typically reduces the amount of data to the very key information. In our case, the signal processing is the automated operational model analysis of the structure, which means to analyze, process the vibration data to extract natural frequencies, mold shape components, and damping ratios. And this is step 1. The step 2 is also very typical, because in long-term monitoring, the big problem we have is that the structural response, be it static or dynamic response, is affected by environmental conditions. It's typically affected also by operational conditions. So, for example, on a bridge, it's affected by the intensity of the traffic, but most of all, the response is affected by environmental conditions. And environmental conditions means temperature above all, and in some cases humidity, in some cases there can be the effect of the wind speed, but temperature is always there. And the effect of temperature is typically much higher than the effect of a damage. And when I talk about the damage, I mean a small damage, because what we want to do is detect the damage before collapse, of course, so it has to be a small damage. So we have to remove these effects. The way that we do that is, let's say, becoming popular in the literature right now, is to construct independent statistical models that link the response of the structure, the one that we store in the observation matrix. The response, I mean the process data. So we build statistical models that link this response of the structure to environmental conditions. So these models are only based on observations, and they are statistical models. For example, in continuous OMA, what we typically find is a linear relationship between natural frequencies and temperature. So you can observe this relationship. You can build a statistical model that links, simple model that links temperature to natural frequencies. And so you have an independent estimate of the natural frequencies, that is this y hat. Again, this can be displacements, whatever. In our case, they are natural frequencies. And if we compute the error of the statistical model, so essentially the difference between the true data, actual data, and the reconstructed data, what you get is something that is not depending on environmental condition. You obtain the residual of the statistical model, and if the statistical model works well, reproduces the variance due to environmental conditions, essentially the residuals are independent on environmental conditions, and so they are suited to build damage-sensitive features and to be inspected for damage detection. So how to make the damage detection? What you have to look for is changes. You have to look for changes in the statistical distributions that are generating the residuals of the statistical model. This is a problem that in multivariate statistical analysis is very common, and the way to solve this is the third step, that is so-called novelty analysis. The novelty analysis is an analysis that highlights a change in a process that is stationary up to a certain point and then deviates from normal conditions. So essentially you compute this. You compute a statistical distance, for example, this t-square, but there are other options in the literature on these residuals, and what you get is a control chart like this. So this shows the statistical distance against versus time. There is a period in which the process is monitored to build the statistical model, so this is called the training period. And in this period you cannot detect any damage, and you have to assume that the structure is behaving in normal conditions. And after the end of the training period, you have the monitoring period. Here, when the statistical distance shows values that were not shown during the training period, it means that there is a deviation from normal conditions. It means that the statistical distribution of the residuals has changed, and it means that the behavior of the structure has changed if the environmental effects have been properly removed. And so here is the damage detection. Here something has happened. Question 1, stage 1, there is something happened on the structure. So we apply this concept in the field of long-term monitoring using accelerations, as I mentioned. And here is the example I was anticipating before. It's a bell tower that is in Perugia, which we have been monitored for 5 years so far. The system is very simple. It's just made of, since the tower essentially has a dynamic behavior that is similar to a cantilever beam, you can monitor, if you're only interested in its natural frequencies, you can monitor it with very small number of sensors. So in this case, the system only comprises 3 accelerometers on top of the tower at the base of the cusp and a couple of temperature sensors. We acquire this data continuously in time, so let's say every 30 minutes we have a data acquisition, so the response of the structure under traffic, wind, normal conditions. And then we process this data with a procedure that makes automatic model identification. I will not give you any detail about this because it would require a talk on its own, but it's possible through some techniques to extract under certain hypotheses, of course, the model parameters of the structure directly from the data. And here you see the environmental effects I was mentioning. In this plot, you see in blue and green the natural frequencies of the first two modes against time in an initial monitoring period, and with red line you see the temperature. You see that essentially the natural frequencies and the temperature are pretty well correlated. And in particular, if you plot frequencies against temperature, you find these kind of plots. You find linear relationship that show in masonry structures typically, especially in towers, what you get is an increase in natural frequencies with increasing temperature due to thermal expansion of the material that closes micro cracks in mortar joints and so on. There are exceptions to this. I'm showing it here, for example, but this is another story. If anybody is interested, we can talk about this later. So here are the 5 years of monitoring. So since December 2014 to this was updated a few months ago, but the monitoring is still ongoing. You see the time evolution of the natural frequencies of 5 modes that we are able to track for this structure. You clearly see seasonal effects with these frequencies that increase in summer and decrease in winter. And you also see strange jumps like these, very, very large jumps. This is ice forming in the micropores of the masonry due to freezing conditions. You typically have this phenomenon once per year, more or less. Okay, these are the process data. Okay, we are in the step 1. This is the observation matrix. If we don't remove the temperature effects, we don't see anything from this plot. But if we remove the temperature effects through the statistical models I mentioned before, and then we construct a control chart, what do we obtain? This is what we obtain for the San Pietro bell tower. This control chart, I feel, is pretty significant. You have the first year, that is the training period. 1 year is needed to observe all the seasonal effects on natural frequencies and to observe the different conditions, let's say in temperature and humidity. After 1 year, the monitoring is active, so you can find deviations from normal conditions. You see, in this first year, we construct a threshold that is associated to a certain probability of exceedance of this statistical distance. For example, we choose a probability of exceedance of 5%. Okay, the blue threshold is exceeded only 5% of the times. If it's exceeded more than 5% of the times, it means that the behavior of the structure has changed. If it has changed, I go and I check. So here you clearly see that the behavior of the structure has changed permanently after August 24, 2016, and again October 26, 2016, and October 30th, and a little bit of January 18th, 2017. And this change is permanent change. So there is a permanent change in the behavior of the structure. What are those dates? You know pretty well. These are the dates of the main shocks of the Central Italy seismic sequence. So what we can say from this plot is that the behavior of the structure has changed after the different shocks of the sequence. So the structure has accumulated some damage. The structure is there, the damage is not visible at all. We have been there several times after the earthquakes to look for visible cues of change in the structural behavior. But what we are talking about is really a slight damage, but still quite visible with this approach. Okay, this we can go fast. It's just to recall about the Central Italy seismic sequence, where I point attention to the fact that in Perugia the accelerations recorded by the Italian strong motion network were really small. So the earthquake was very strong, close to the epicenter, as we know, but in Perugia it was very weak, at least in terms of potential damage to structures. But if we do, of course, then we did some linear dynamic analysis to understand if what we observe from the monitoring system makes sense. And what we expect is this damage being accumulated in the structure after the first, the second, and the third shock of main shocks of the sequence. What we expect is some damage in the belfry, which of course is the most vulnerable part of the structure. And from our analysis, we can also find some reasonable confirmation of what we obtained from the monitoring system, so that the biggest changes in the natural frequencies are expected on the torsional mode. So if you see here the change in natural frequency of the torsional mode obtained from the monitoring system and expected from the numerical analysis, they are very similar. And actually, if you look at the plots, you see that the temperature frequency, the frequency temperature plots, they have changed in a quite evident way before and after the earthquake. So there is a shift in all the natural frequencies of the structure. And here is a change in the statistical distribution of the residuals of the statistical model. So what are we doing in Gubbio? I think this explains what we are doing in Gubbio. So I wanted to show these results to demonstrate what's the meaning of what we are doing. With this kind of approaches, we are studying this building, the Consoli Palace. It's a very important palace. Many of you are from Umbria, and you all know the importance of this palace belonging to the Middle Ages. It's a very interesting architectural piece that has several problems from a structural engineering perspective. The palace shows a moderate state of damage. There is a clear crack pattern that was surveyed by our research group, and tomorrow there will be a presentation from Professor Nicola Cavalagli that will go into the details of the crack pattern survey and the structural analysis. I will not in this case. I'm just highlighting that there are a couple of major local collapse mechanisms that we have identified. One is the overturning of the main facade of the building, and the other one is the overturning of a corner on the north side. So to understand if these mechanisms are activating, we are monitoring two major cracks using two crack meter sensors that measure the amplitudes of these cracks. And also we are doing vibration monitoring, as I will show you in a while. Another problem suffered by the Palazzo dei Consoli is material degradation due to the exposure of the stones to climate forcing and to climate change. This is also object of the presentation of Professor Cavalagli tomorrow, so I'm not anticipating anything on this. We are doing vibration monitoring, which means that we are using vibrations to understanding the behavior of a building. This is not typical. This is done for towers, because of course towers are slender masonry structures, but for buildings this is kind of unusual. Of course this is pretty high building, so a relatively flexible one, but there is not much literature on the use of these methods for these kind of structures. However, you can see here that with an ambient vibration test on the structure, we can fairly well identify at least 6 modes of vibration. Maybe we can identify more, but let's say we do identify 6 modes of vibration, and this information is very interesting for calibrating models of the structure. We have performed other types of on-site investigations, which I'm not presenting here. I just would like to stress the importance of doing ambient vibration tests, so vibration measurements, to tune and calibrate numerical models of these kind of structures. Here is a calibration of a linear finite element model of the building, where you can see that based on the results of the ambient vibration test, we can update the uncertain parameters of the structure and get a very good agreement between identified and numerically predicted natural frequencies with an average error of about 2%. But let's stay to the monitoring. Again, the structural analysis aspects are covered in the talk of Nicola tomorrow. Again, the monitoring system. We want to do it very low cost and continuous. So we are monitoring these 2 cracks, as I mentioned before, to understand if these mechanisms are activating or not. Every crack meter sensor also mounts a temperature sensor, because of course we have to remove the temperature effects. And then we are monitoring the evolution of the natural frequencies of the building, just as we did for the San Pietro Bell Tower. And to do that, in this case, we are using, again, a very small number of accelerometers. We need to track 6 modes, and this is possible with just 3 sensors on top of the Palazzo dei Consoli. Of course, if you want to do damage localization, then you need to typically you need to increase the number of sensors. But if you are just interested in the first question, this can be enough. So here a little bit of results. You see the amplitudes of the two cracks of crack 1 and crack 2, the two cracks related to the main mechanisms. Over time, you see that the monitoring started in July 2017, and this plot was updated until a few days ago. These data are continuously acquired, and then through the internet they go to the Heracles platform, that is this ICT platform that Dr. Padeletti introduced at the beginning of this afternoon. And you will see a presentation tomorrow by a colleague from Fraunhofer, Germany, that will show this platform in action. So these data directly go into the platform. Here you see that there are clear seasonal effects on these cracks, and in particular, going from summer to winter, the cracks open. And this is due to the fact that the material, the volume of the material decreases, and so the cracks, if they are pass-through cracks, they open. And you see that the amplitudes of opening and closing of the two cracks is very similar, and you also see clear daily effects on these crack amplitudes. But we need to remove these effects if we want to find any unexpected behavior. So this is what happens after we compensate temperature effects. You see that the compensated crack amplitudes are reasonably stationary in the monitoring period. So from this data up to now, what we can say is that we do not see any major movement. Of course, the more data we acquire, the more interesting conclusions we get in the future. But what we can say from this plot is we don't observe any evident movement in the structure. How did we remove these temperature effects? Through a statistical model like this one. In this slide, you see in dark blue the measured crack amplitudes 1 and 2, and with light blue you see the results of the statistical model. So light blue is a function of temperature, not the reading of the sensor. The dark blue is the reading of the sensor. If you take the difference between these two quantities, you get the residual. And if you sum the average value to the residual, you get the crack amplitudes after temperature compensation. We can build a control chart, as we did on the San Pietro Bell Tower, and here is the control chart. The first year, again, is a training period, and then there is the observation period. We don't see anything special here. We don't see any particular deviation. Of course, the statistical models have to be improved, because this kind of behavior here means that some removal of environmental effects is not perfect, but this is not the time to talk about these aspects. Anyway, you don't see any evidence of change in behavior of the structure. And we have done the same with natural frequencies. Here you see the plot of the 6 natural frequencies that we are able to track on this building. Again, you see clear daily effects. And by the way, here there is a temperature effect that is the opposite than the one we observed on the San Pietro Bell Tower. So this is also interesting from a theoretical point of view. But in any case, from this plot, we have to remove the temperature effects again. So here I show you the plot after temperature compensation. You should see that, for example, if you look at this frequency here, you should see the seasonal effects. And after compensation, you should see that these effects disappear. Of course, you will notice this big jump. Again, this is freezing. We are not compensating freezing here. It's possible to do it. We are just not doing it here because freezing is not a condition that is particularly frequent in our climate zone. So it's not that important to compensate these effects, but of course it's possible. Anyway, you see that the seasonal effects associated to the summer and the winter are removed. And again, how? Using statistical models like this one. Here you see predicted versus reconstructed versus identified natural frequencies. And again, we build a control chart to understand if the process is stationary, if the behavior of the structure is changing. Again, we don't see anything special from this plot. So we did not evidence any anomaly in the behavior of the Consoli Palace so far. I just could mention that here, you see, this is kind of an anomaly. There were some restoration works on the building during those days, so we suspect that was the reason for this deviation. And this is the freezing, but no main events. Quickly, the Gubbio town walls. We saw this survey already made by our colleagues from Aegeos, done through drones. Why are these surveys very important? Because from these surveys we can extract geometrical informations that are very important for our structural analysis. So here you see extraction of one section and a simple structural analysis that computes the critical level of the soil against the critical level of the water inside the soil that determines the collapse of the wall in no earthquake conditions and in earthquake conditions with increasing seismic intensity. These kind of plots are used in the ICT Heracles platform to understand when soil accumulation becomes critical. What you see here is even with a very small earthquake, these walls are not safe. We are already below the current height of the soil. So if there is a small earthquake, we expect possible collapses in the Gubbio town walls. Are these kind of collapses is it really possible to monitor and to anticipate these kind of collapses? We don't know, because when the crisis is fragile, it's very hard to anticipate these type of problems through monitoring. Anyway, some kind of movements maybe could be anticipated, and for this reason we decided within the Heracles project to monitor the walls using inclinometers. So what we did is we identified, together with Comune di Gubbio, some critical zones in the walls, as you saw also in the presentation of Dr. Padeletti, and in these zones we have installed inclinometer sensors, wireless inclinometer sensors, that acquire data continuously and send this data to the data acquisition system that is inside the Consoli Palace, and from there through the internet to the ICT platform, Heracles platform. So far this is only data. There are no conclusions because the monitoring started a few months ago. Here you see a plot of the measurement of inclinometer number 1 that is measuring. This is temperature measured within close to the sensor, and this is the measurement of the inclinometer in angle. So what you see is that the wall is moving towards the mountain with decreasing temperature. But we don't have 1 year of data, so we cannot really make conclusions. Here you see in zone 3 and 4 a similar behavior. We have some drops here. These are problems associated to unexpected event, critical event, but caused by humans. There was some vandalism attack. These problems happen in monitoring action. Interestingly, in zone 4 and zone 5, we have an opposite behavior. So this is the region where we have the highest soil level. That Giuseppina knows very well because she knows this area quite well. And here we have the opposite behavior. So with decreasing temperature, the wall is going down. But this could be simply a temperature effect, so we cannot conclude anything right now on the stability of the walls. So to conclude, we have demonstrated a little bit of potential of long-term monitoring, especially vibration-based monitoring, in application to cultural heritage and in particular to the case studies of the Consoli Palace, and with this I thank you very much for your attention. So now I again switch the chair. Alright, so I introduce the next speaker, that is also from our group, Professor Ilaria Venanzi. I mentioned that there would have been talks on damage localization, so this is the first one. Seismic damage localization in historic structures through online finite element model calculation.
Thank you, Filippo. Good afternoon, everybody. You have already heard from the previous presentation that the use of long-term structural health monitoring systems allows to highlight if a structure has undergone permanent damage after an earthquake, or to verify if it is accumulating damage or if the damaging process is accelerating. While damage detection can be considered essentially a data-driven process, damage localization typically requires a finite element model in order to link model parameters to damage-dependent mechanical quantities. In this context, I represent a quick automated procedure for damage detection and localization based on online finite element model calibration, and I will also show its validation based on simulated and real field monitoring data relative to an historic civic tower. The first step of the methodology is the construction of a reliable finite element model of the structure based on the results of ambient vibration tests, and the step consists in building a surrogate model relating the model parameters to damage-dependent mechanical parameters. Then operational model analysis is performed at specific time intervals using monitoring data, for example by stochastic subspace identification. Frequency fluctuations are removed, as we heard before, in order to depurate data from thermal effects. Frequency tracking is then performed to detect the eventual onset of damage in the structure. If damage is detected, in order to localize the damage, an inverse model calibration problem is solved by using the surrogate model in order to evaluate and localize the modification of the damage-dependent mechanical parameters in some macro elements in which the structure has been ideally subdivided. This can be done by solving an optimization problem in which the objective function is related to natural frequency decays and modifications in eigenvector components. Going a little bit more in detail into the optimization problem, if U is a vector storing the damage-related mechanical parameters for the different macro elements of the structure, the problem consists in minimizing a functional J, which is a linear combination of two terms, one related to the difference between the experimental and the numerical frequency decays, and one related to the model assurance criterion coefficients between experimental and numerical mode shapes. The problem is solved by repeatedly solving model analysis exploiting the finite element model, but when the computational time required by this operation is too high, it's greater than the time interval between two subsequent identifications, a surrogate model can be adopted in order to reduce the computational effort. The surrogate model is essentially a relationship between model parameters and design variables. The methodology has been applied to the Shiri Tower, which is a 41 meters high civic tower located in the historic center of Perugia. The tower has an almost square cross section with about 7 meters side length, and it is surrounded by building aggregate up to the height of about 18 meters. The material is homogeneous and regular limestone masonry. Ambient vibration tests were carried out in May 2017 in order to identify the model parameters of the structure. To this aim, 12 high sensitivity uniaxial accelerometers were installed on levels 1, 3, 4 and 5 of the tower as shown in the figure, in order to measure microtremors induced by traffic and humidity. 7 vibration modes were identified, 4 flexural modes in the northwest and southwest directions, 1 torsional mode, and 2 higher order flexural modes. The Shiri Tower has been monitored preliminarily for 1 week in January 2017 and then continuously since December 2017 to present. The monitoring system is made of 3 accelerometers located at level 2 and 2 thermocouples installed at levels 2 and 1 indoor and 1 outdoor respectively, in order to allow removal of thermal effects. A Wi-Fi data transmission system allows to transfer data from the Sherry Tower to the Laboratory of Structural Dynamics of University of Perugia, where records are continuously processed and stored. A finite element model of the tower and the surrounding buildings has been constructed. A free mesh of solid tetrahedral elements has been adopted, and the materials are elastic and isotropic. The preliminary calibration has been carried out based on the results, the experimental results of ambient vibration tests. A total of 20 different materials have been assigned to the model in order to differentiate between walls and floors, each one having a different elastic modulus and mass density. The calibration has been carried out by dating the parameters by using modal sensitivity coefficients. Here is shown the comparison between the identified numerical natural frequency as well as the Mach coefficients, and results show an overall good agreement between model and field data. To apply the procedure, the finite element model has been subdivided into 4 different macro elements. Macro element 1 is the building aggregate and a portion of the tower up to the top height of the roof of the aggregate. Macro elements 2, 3, and 4 are the parts of the tower over the height of the top of the aggregate. The damage-dependent parameters, those which are identified through the localization procedure, are stored in this vector U, which collects the coefficients multiplying the nominal values of the elastic moduli of the 4 different parts of the building. In order to reduce the computational effort, a surrogate model has been adopted, and in particular a quadratic relationship has been chosen to model the relation between model parameters and design variables and uncertain parameters. As shown in the figures, this model, this quadratic model, shows to be reasonably suitable to reproduce the variation of the model parameters in the neighborhood of the nominal values of the design variables. In the optimization problem, the lower and upper bounds of the design variables are 0 and 1 respectively. 0 means complete damage to the element. 1 means no damage occurred to the element. In the delta term of the objective function, the Mach is computed between experimental and surrogate models modes. In the epsilon term of the objective function, delta Fi exp are the experimental frequency decays obtained with respect to the mean value of the identified resonant frequencies in the training period, in the preliminary training period, set equal to 1 year. And delta Fm are the differences between natural frequencies of surrogate model and finite element model. The algorithm selected for the optimization is the genetic algorithm. 3 different damage scenarios have been simulated in order to verify the effectiveness of the procedure. Damage 1 is a localized damage at the contact between the tower and the aggregate, obtained by reducing by the 20% the elastic modulus of the red part, of the green part of the tower as it's visible from the figure. Damage 2 is a diffuse damage in macroelement 3, obtained by reducing by the 40% the elastic modulus of the blue part of the tower. Damage 3 is a localized damage in a masonry wedge at the top of the tower, possibly related, this type of damage, to the lateral thrust of the top bolt, which is obtained with a 40% reduction of the elastic modulus in the red part of the tower. In the table are shown the frequency decays obtained in the 3 damage situations. Frequency decays which vary between 0.01% to 4%. And in this table are shown the results of the localization procedure, respectively for D1, D2, and D3. And for different combinations of the weighting factors, weighting coefficients of the 2 terms of the objective function, the one related to frequency decays and the one related to mode shapes. For damage type D1, the only parameter which varies is K2, which is smaller than 1, showing that damage occurred on macroelement 2 at the contact between the aggregate and the tower. For damage type D2, the coefficient that experiences the highest variation is K3, showing that damage is mainly concentrated in the macroelement 3. And finally, for D3, only K4 is smaller than 1 as damage occurred on top of the structure. Some misleading solutions are observed in the cases when the coefficient alpha is much smaller than the coefficient beta, showing that this second term of the objective function, the one related to mode shapes, is important as it allows to avoid false positive, to avoid non-physical solutions, and therefore for studying the robustness of the solution. It's also necessary to point out that the contribution of this second term would be much more important in the cases when a larger number of sensors are used, because in this case we have 3 accelerometers located at a single level of the structure. The procedure has also been applied for tracking the parameters, for localizing the damage in time. To this aim, preliminarily, the identified natural frequencies are depurated from the thermal effects, and here are shown the identified, predicted, and depurated natural frequencies as a result of the application of the multiple linear regression method that we heard before. To these identified and depurated frequencies, the frequency decays corresponding to damage scenario D1 have been applied, as shown in this graph. The application of this frequency decays is done after 1 month after the end of the training period of 1 year. And here are shown the results in terms of damage-dependent parameters related to the previously shown frequency decays. It's possible to observe that the parameter which experiences the highest variation and most clear variation is K2, confirming that damage is located in macroelement 2. To further validate the procedure, also real earthquake-induced damage has been adopted. Indeed, during the preliminary monitoring period of the tower, An important seismic sequence occurred with epicenters close to L'Aquila. The seismic sequence did not produce an important damage to the tower, but led to non-negligible variations of natural frequencies, as it is possible to see in these two graphs. The table on the right-hand side shows the frequency decays obtained correspondence of the earthquake of the seismic sequence of January 18th, 2017. And here are shown the results of the localization procedure. Only the coefficient K2 is smaller than 1, showing that the damage is occurred at the contact between the tower and the aggregate, and this is possibly due to different small different deformations experienced by the two parts of the structure. Of course, are small damages, but still noticed from the localization procedure. Finally, also nonlinear dynamic analysis been carried out, and to this aim, a nonlinear finite element model has been built in which a suitable damage concrete plasticity model is adopted for the masonry. To the model, a time series of the two concatenated accelerogram of the two main shocks recorded by the closest seismic station to the Shiri Tower have been applied. And this time series, these accelerograms, have been scaled in order to reproduce the peak response acceleration which was measured by the monitoring system on the top of the tower. This figure shows the map of the tension damage as a result of the nonlinear dynamic analysis, confirming that the most vulnerable, the most sensible part of the structure is the one at the contact between the tower and the aggregate. This was also confirmed by visual inspections that allowed to verify that small cracks, as it's visible in the top figures, in the top pictures, were observed by the building occupants as a consequence of the seismic sequence. So in conclusion, a methodology for earthquake-induced damage detection and localization in masonry towers using long-term vibration monitoring data and online finite element model calibration is presented. And the methodology has been applied to the Shiri Tower, and simulated and real damage scenarios have been used in order to validate the procedure. Further development of this work will consist in trying to use different surrogate models in order to refine the results of the localization, and will consist in using data from a larger number of sensors. We have already installed more sensors on the Shiri towers, which are measuring since a few days ago, maybe 1 month. So we'll be able to study the influence of a larger number of sensors in the localization procedure. I wish to thank my co-authors, which are Alba Anchita, Nicola Cavallai, Laura Ierimonti, and Filippo Ubertini, who took part on the project, and I would like to thank you all for your attention.
Thank you very much, Ilaria. And thank you also for giving the talk in a condition that was that is not optimal, unfortunately. Okay, so we continue with the group of University of Perugia. Enrique Garcia Macias, postdoc here in our group, will also talk about localization. with an approach, with damage localization, with an approach that is complementary to the one we have seen from the speech of Professor Venanzi. So we will talk about seismic interferometry for SHM of historic structures. Thank you.
Good afternoon. Thanks you all for coming. It's very nice that this presentation comes after the presentation of Ilaria, because we are treating similar problems. In this case, I will focus on detection and localization of damage, but in this case we don't really need to use any kind of model, and we can work directly with the data. And I will talk about the application of seismic interferometry for SHM of historic structures. The presentation outline is divided as follows. First, I will give a general introduction to these techniques. Afterwards, I will give a brief overview of its theoretical framework. And finally, some application examples, very recent, that we have developed in a case of an isolated masonry tower, and some analysis of ambient vibration test in the Scilly Tower, Consoli Palazzo, and in San Pietro del Tower. And finally, some very recent ongoing research works we have been conducted on the continuous monitoring of the Scilly Tower here in Perugia. And finally, some conclusions. Where these techniques are not new at all. Actually, it comes from geophysics, and the first pilot applications of these techniques date back to the beginning of the last century during the First World War, in which it was applied to detect enemy submarines and artillery. However, it was in the 20s when its benefits for the petroleum industry boosted its use ever since. For example, I show here a sketch in the book The Petroleum Handbook, published by the company Shell in 1948, in which it shows how a seismic input by using dynamite can be used and analyzed to study the reflections of the waves, and so identify the presence of oil or gas deposits. In the figure on the right hand of the slides, you can see a photograph of a monument in Oklahoma commemorating the first successful application of a seismograph by the company, American company Geological Engineering, and led by Professor J.C. Karcher, who showed for the first time in history that it is possible to study the reflection of the waves and so identify the subsurface of the Earth, and so identify the presence of oil deposits. A good definition of this technique was given by Schuster and co-authors, and it claims seismic interferometry is the process of cross-correlating seismic traces recorded at different locations of the Earth's surface with the aim of retrieving information about the surface. In order to illustrate this definition, let's focus on a very simple example. Here I have a network of two sensors located at positions A and B, and an input source buried in the subsurface at position XS. If a wave is emitted by the source, it reaches first the sensor A. When it reaches the surface, it reflects back until a diffractor at position XT, which can represent the interface between two different geological strata. Here, a part of the energy is reflected until it reaches the position of sensor B. And the question here is how can I detect the time delay of the waves going between sensor A and sensor B. So if I cross-correlate the recorded signals by these two sensors, I get a pulse like that one, in which it has a time shift which corresponds to the time delay between the position of the wave at sensor A and sensor B. So this very simple example illustrates one of the most essential aspects of this technology, is that all the time shifts that I measure are relative to a reference state. It means that I don't really need to know the position of the physical source. In practice, geophysics must deal with very complex problems like that one shown there, with different strata, with different impedance characteristics, complex reflections. But applying, for example, relations like that one, in which I can relate the impedance of the material, which is the density multiplied by the velocity of the propagation, and applying the Snell's law to identify and relate the angle of the incident wavefront and the refracted one, as well as the energy partition between refracted and reflected waves, we can trace all the ray paths of the waves traveling throughout the subsurface of the Earth. And applying a similar cross-correlation technique that one shown in the first sample, we can detect all the time delays. And here, if I really find some kind of boundary conditions, we can pose an inverse problem and identify the wave velocities in the subsurface of the Earth. Here, for example, I show very nice results reported by Lin and co-authors who identified in a bidimensional way the wave velocities distribution in the southern coast of California by using the waves, superficial waves imposed by the ocean. This concept can be extended to the three-dimensional case, for example, in this work of Dragunov and co-authors, who identified a large section in Libya of a portion of the terrain of about 20 by 3 square kilometers and a depth of around 2 kilometers. And here it is easy to see that there are different strata of the Earth as contrasts in the wave velocities. So the big question here is, can we apply this technology to the monitoring of building structures? This is a novelty actually, because the technology is not that new. But the challenge is here, how can I apply this technique to monitoring buildings? In order to give an answer to these questions, let's have a look at its theoretical framework. And if we consider a building with a simple model like that one, it's a multi-layer medium in which the waves can travel with different velocities depending on the physical properties of the sections of the structure. The objective and the goal that I must reach is how I can correlate the signals that I measure with a network of sensors deployed all along the structure. And one possibility is applying the convolution interferometry. In here, I correlate all the signals with a given reference state, which is often called a virtual source, which doesn't need to correspond to the physical source. It means that I don't really care about the origin of the waves. So I can apply this technique for seismic inputs or ambient vibrations. Well, just a quick look into the detailed mathematical formulation of this problem. I can relate the records by an arbitrary sensor as the convolution of a reference state. This is a reference sensor that I choose with so-called impulse response functions, which are simply the inverse Fourier transform of the transfer functions. So here, actually, what I'm getting is the response of the structure in time when I have a delta Dirac impulse at the reference state. So somehow I'm trying to obtain the Green's functions of the system. We can define more sophisticated expressions like that one, which include a regularization parameter in order to avoid numerical instabilities. But the physical framework is this one. It's not extremely complex. It can be as simple as this. So if I represent the impulse response functions all along the height of the structure, I can trace the real paths of the waves traveling all along the building. Here, by a simple peak-picking analysis, I can get the arrival times and let this define the velocities between every pair of sensors. If we consider, and it is like this, that the velocity of the waves depend on the physical properties of the building, all these magnitudes are physically related to the physical properties of the structure, and these are local magnitudes. It means that if I get a variation in some of these parameters, I have an indirect evaluation of the variation of the local stiffness of the structure. This is a simple scheme of the methodology, in which first I compute the Fourier transform of all the records of the sensors, then we get the transfer functions, considering one of the sensors as a reference state or a virtual source. We apply some filtering, and by applying inverse Fourier transform, we directly get the impulse response functions. So until now, the methodology is exactly the same as that one used from geophysics, but the differences come here. Let's have a look at the velocity of the waves. If we consider that the building can behave as a Timoshenko beam, cantilever Timoshenko beam, and we assume an harmonic solution for the displacements or accelerations, we can solve the differential equation of the problem, and we get this equation. The only thing that I would like you to know in this equation is that there is a relationship between the wave number, which is the variable k, and the frequency. It means that the velocity of the waves change with frequency. This is a dispersive medium. So we can define different types of velocities. In this case, typically we define the phase and group velocities. And instead of looking at the mathematical expressions, let's have a look at this video, in which the phase velocities are the green dots and represent the velocity of the impulses contained in the waveform, while the group velocities represent the velocity of the envelopes of the waveforms. In a slender structure like a masonry tower, we usually have dispersive curves like that one shown on the left side of the slide. And here we can observe that the phase velocities are usually smaller than the group velocities. And second, for low frequencies, the velocity of the waves change a lot, and it reaches a point at moderate or high frequencies in which the velocities tend to reach an asymptotic value. So we have to deal with seismic waves, and this is a big problem. For example, if we study P waves, longitudinal waves, which are the fastest one, the velocities of these waves are around 1,000 meters per second. It is true that in buildings, the velocity gets considerably smaller, like in that case shown by Ibrahim and co-authors of application of this technology to a reinforced concrete building, in which the velocity was around 500 meters per second. So this is still outstandingly huge. So a direct conclusion of this analysis is that the sampling frequency is going to be a big deal in this problem. So on this basis, we have developed some analyses which are most of them very preliminary. For example, here we studied a finite element code of isolated masonry tower subjected to seismic inputs. Here we consider 3 different sections separated by both acceleration and strain transducers and subjected to synthetic accelerometers at the base. Applying the convolution interferometry technique, we can get waveforms like this shown in the slide. If we consider a virtual source at the roof level, we have 2 causal and acausal waves. A group of waves going upward, coming from the base, reflected at the roof, and reflected back until the base. If we consider a virtual source at the base level, we only have causal waves, so waves going upward from the base and reflecting at the roof. So it means that the analysis of these waveforms represent the physical behavior of the dynamic mechanisms undergoing this problem. We also conducted nonlinear dynamic analysis with earthquakes with increasing damage severities. And by a simple peak-peaking analysis, just taking the maximum values of these impulses, we got variations of the wave velocities for different peak ground accelerations. And it is observed that the larger variations are found at the base level, which correlates well with the identified damage patterns in the numerical model. Also, it is observed in the figure on the right hand that the variation of the velocity of the waves increases with the big ground acceleration. So a conclusion of this first analysis is that this technique can be used in a fully data-driven way and allows us to identify damage, that is detection, localization, and to some extent also quantification of the damage. This technique can be also applied for ambient noise, the convolution interferometry. Here we apply this technique to the Shiri Tower, in which we monitor 2 orthogonal directions of the tower with 11 sensors. And applying this technique that I mentioned before, we obtained these waveforms, which are slightly different to those that I showed before. In this case, we have 2 causal and acausal waveforms, considering both virtual sources at the base level and at the roof level. It means that we don't have now one single input at the base, but we have multiple sources all along the building. We have wind actions, we have human activities that indicates this behavior. Also applying different bands of filtering, we can get the dispersion curves from an experimental point of view in both orthogonal directions. And here it is interesting to note in the figure on the right hand that in this direction the velocity of the waves are considerably larger, what means that the contribution of the building aggregate in terms of stiffness in this direction is larger. If we interpolate the results of these waves or for different positions of the sensors, we get these videos in which we can see, for example, in the blue line with a filter from 9 to 14 Hz, in which a first pulse beginning at the roof splits into two pulses, and we can see clearly how the propagation of the waves behave here. All the rest of the dynamical features can be also obtained with this technique, for example, the mode shapes and the damping ratios. If we isolate the frequency bands of the first two resonant frequencies, bending modes, here I show, for example, the waves from 1.6 to 1.8 Hz and 4.8 to 5.8 Hz. If we get the amplitude of the waves at time zero, we get directly the representation of the mode shapes, which correlates well with those shown on the left of the slide, which were obtained with a normal stochastic subspace identification. Also, we can get the damping ratio by studying the decay of the amplitude of the waves, like shown in the last figure. We also applied this technique to the consoling palace, and this case is especially challenging. First, because it's not very tall, it's not very high rise, so it's a problem in terms of sampling frequency, but also the geometry of the building yields not very linear propagation behavior. In any case, we could obtain as well two different pulses propagating in the building. It is true that it is difficult, it's very challenging to obtain pulses in the middle section. Here, for example, you can see that the first pulses doesn't split into two until almost the end of the tower of the structure. So here we can detect damage, but really locate damage is not very feasible. We also applied this technique to the San Pietro Tower that Filippo mentioned before. And the idea of this analysis is to see if with this technique we can detect the damages that they reported that appear during the sequence of 2016 in central Italy. And to do so, we applied this technique to two different ambient vibration tests conducted in 2015 and 2017, so before and after the central seismic sequence. Here I show also the representation of the waves. In this case, you can see that the first pulse splits into two before, so we can really detect and localize damage in this case. So if we compute the velocity of the waves by a very simple peak-peaking analysis, and we consider, for example, only the section of the shaft at the belfry, here reductions of around 10% are observed in the wave velocity. So it means that we have a loss of stiffness after the seismic shock. If we consider only the belfry, larger differences are observed, around 20%. So it means that the damage is localized there, which correlates well with the numerical simulations conducted in previous analysis. And finally, some ongoing research works that we are conducting. This is super preliminary. Actually, we removed all the sensors last Friday, so what I'm showing here is just very preliminary. Don't take it too seriously. We deployed 12 sensors at different heights of the tower with the idea of applying seismic interferometry along with normal OMA. So the idea is to generate a synergetic monitoring system in which, on one hand, we detect the natural frequencies, but on the other hand, we have a fully data-driven approach to detect damage. Here are some first preliminary results of the identification of the resonant frequencies and the relationship with temperature, and some waves that we recently obtained. Here I show waves considering virtual sources at the base and at the roof level for a sampling frequency of 200 Hz. Here it's observed that the waves look nice, but if you see the time series of the arrival times of the waves in time, it is observed that it's ultra peaky. It has so many peaks. So the resolution of this graph is not very good because of the high velocity of the waves. We also conducted analysis with 1000 Hz and 5000 Hz of sampling frequency that I have to still post-process, and I hope they will get better results. And finally, some conclusions. Seismic interferometry considers the dynamic response of the structures as a superposition of traveling waves and exploits wave delays to infer local damage. This is very interesting because actually we are not really inventing anything new. It's just a way of looking at the dynamic behavior of the structures in a different perspective. But actually we need the same equipment, we need almost the same procedure for the monitoring of the structures. It's just a matter of looking the angle of the analysis. This methodology can be easily implemented through the peak peaking analysis of arrival times. That is to say, this technology can be fully data-driven. It's actually not very expensive in terms of computational demands. It can even implement it directly in the data acquisition system. Given that the wave delays are obtained relative terms to a certain reference position or virtual source, the assessed wave delays do not depend on the soil structure interaction. So we are only monitoring the structure irrespective of the connection with the foundation. The conducted numerical studies demonstrate that this methodology is apt for damage identification, that is damage detection, localization, and to some extent quantification. And there are still some open issues, such as the limitations that I mentioned before on the sampling frequency, data management of the acceleration records, etc. Thank you.
Thank you very much, Dr. Garcia, for the excellent talk. We are closing the session now with the last talk from the Perugia group for today. It's Professor Cruni. Co-authors are Professor Busella and Professor Vinti, that are sitting here in the first row. This is also a work that is multidisciplinary, because Professor Vinti is a professor of mathematical analysis. And so you see that engineers effectively collaborate with other professors from other disciplines. So the talk is on thermographic analysis of plastered masonry walls. Thank you.
Thank you, Filippo, for your introduction. Good afternoon to everybody. In my talk, I will present you the results we obtained in research together with Vittorio Busella and Gianluca Vinti. And our aim in our research is to develop a method to identify the texture of masonry walls or plastered masonry walls with non-destructive techniques. This is a summary of our idea. We want to be able to take a thermography of a masonry wall, then to perform an image reconstruction, an image enhancement of the image resolution, then to perform texture identification. With the term texture, I mean the arrangement, the modular arrangement of the two phases which constitutes the masonry. We want to know where the stones are and where the mortar joints are. Then, once the texture has been identified, we perform an homogenization in order to obtain material which could be used in a fine element code to assess the seismic vulnerability. In this slide, this step is shown in green, since I will not deal with it. So I will stop just here. Why we are interested in this approach, why we think that this could be useful? Because the method that we propose is a non-destructive method. In this slide, on the right, have shown probably the most destructive test that we can perform on the masonry, which in fact is usually made on masonry wall that had to be torn down. So we want to be able to characterize the mechanical behavior of the masonry without perform an invasive test. Ideally, just take a thermographic image and use simple instruments to estimate the characteristics of the phases. What is the idea of thermography? And this is important also to understand why, when we can use it and when not. The idea is that one of the phases of the idea is that when one of the faces of the measuring world is heated, then we have a heat flux toward the non-heated surface, and this heat flux depends on the phase. For example, we can have a greater flux across in this case, the brick, and smaller flux on the mortar joints. With thermography, which converts this heat flux in a temperature map, we have an infrared sensor which detects the temperature. We can identify the different phases. The interesting thing is that even if the measure is covered with the plaster, we can see what are the texture behind the plaster. Obviously, there are some limits. For example, as I will show you later, in the case that the heat flux is not consistent, we do not obtain thermic images which can be useful. Also, if the external surface of the wall, for example, in this case exposed to the sun, is subjected to a strong wind, we can detect the phase in a useful way. The main thing is that the heat flux should depend only on the material. In this slide, I show you the first result that we obtained. On the left, we have an image taken with a conventional camera. On the right, we have a thermographic image. On the right, we can see one of the many ways the thermography can be useful to a civil engineering. The classical uses are to detect the heat bridges in the buildings, or to detect, for example, the moisture content of the walls. In this case, we see that in the case of thermography, we see that there is a closed window that has completely different texture with respect to the structure of one. Obviously, this is an important information from the structural point of view, since this covered window do not contribute to the structural response. And the memory of this opening was completely lost. I can assure you, since this is my house, so I didn't know there was a window there. The other aspect that we use on the thermographic image is that it can be used to detect the different measure which the house is made of. In this case, we see that this is a building that was made in 60s, so as typical in those years. The first floor is made of stone masonry, and the second is made with tough masonry. So we have two different textures, a chaotic one at the lower level and almost periodic one at the upper level, with two different stones. In order to investigate the potentialities of this approach, we have started a research program which has several steps. At first, we have designed some measured wall samples in order to perform experimental tests. we have taken a digital image of these samples, then we have covered them with plaster, both faces. We have taken thermographic images, enhanced them, identified the texture, comparing the results with those obtained in the visible range. We have evaluated the mechanical characteristic through homogenization, and finally we have evaluated the influence of environmental parameters. These are the measured samples as designed. We have on the left the periodic texture, so we have a block of equal size arranged in a periodic pattern. On the middle we have a quasi-periodic texture in which the rows have the same height, but the stones inside the rows have different width. While on the right we have a random chaotic texture. We have built these samples with standard uni bricks taken as a wall or cut in half or in 4 pieces, as shown on the bottom. This is because we wanted a design which allowed to build several measuring samples with the same texture. These are the photos taken with the conventional camera. Just a note that we have realized the samples slightly smaller than what we thought, in order to make them, in order that we can transport them with more easily. So the final dimensions are about 75 centimeters. We have covered them with 1 centimeter plaster, so this is the image of the sample. If you are interested, the 3 samples are located now on the opposite side of the courtyard, so they are there. Please do not go toward them in order to not harm yourself. Okay, then what we did is take a thermographic image on the left. We have converted it in grayscale, and then we enhanced its resolution. The original image is 200 pixels per side, while the enhanced one is 400 pixels per side. In order to enhance this image, we applied the findings of the sampling theory. I will not go into much detail here, just that we are able to increase the resolution by choosing a kernel. In this case, we use the Jackson kernel, and this is the results. So we have the original image, the original in the sense of the reconstructed image, and we want to separate the face, so identify which pixels are of mortar and which pixels are of bricks. So we applied the techniques of image processing. So we applied the median filter, then we thresholded the image to pass from grayscale to a black and white image. In this case, we adopted an adaptive thresholding, since we have found that it's almost impossible to take an image in the real world that is not subject to a gradient of luminance. So we have to adopt a threshold, an adaptive thresholding, in order to not take account this gradient. Then we have, as we can see, the thresholding typically forms some imperfection. For example, we have mortar inside the stones, which is obviously impossible. So we have technique to fill the holes, and then we apply the erosion and dilation operators in order to smooth the contour of the stones. So we have achieved a consistent separation of the faces. We know where the stones and the mortar are. Obviously there are still some imperfections, such as some connection between the stones which are not real, but this is the best that we could obtain. In order to estimate the mechanical characteristic of the measure, we have used the test window approach for homogenization. So we applied, we seek the relation between the mean value of stress and the mean value of strain, and this relation is expressed in terms of stiffness matrix. Since the dimension of the since we are not sure that the dimension of the measuring panels are those of the representative volume element, we applied two different sets of boundary conditions, one in terms of tension and the others in terms of displacement. These two different boundary conditions give two different estimates of the stiffness matrix, which can be used to estimate the mean, which we assume the effective stiffness matrix. There is the literature that told us that as the dimension of the window increases, these two estimates converge to the effective estimates. So in this slide we reported the results for the estimate of the overall window and smaller windows that shows us that the effective estimate is quite stable, and obviously as the dimension of the windows are smaller, we have more dispersed results. The last thing that we have done until now is that since that the thermocamera store the information in a sort of a raw format, the same to give the idea, just if you have a reflex camera, you know that if you save the image in a raw format, then you at the computer can adjust, for example, the white balance or other parameters in order to have a better image. In this case, we were able to modify the temperature range measured from the camera. So these are the results that we obtained for different temperature range. The interesting thing is that the estimate is quite stable, even if the parameters, the effective parameters, are not known with sufficiently knowledge. So we are quite confident that the estimate is a good one. We have still in our research, so there are more things to do, but the results that we obtained, that I briefly recall here, tell us that this could be a good approach to obtain the mechanical characteristics of the measuring without resorting to destructive tests. So we hope that this could be this could be good also for practical engineering application. Thank you for your attention.
Thank you very much, Professor Tuni. So this was the last presentation of the day. I would like to thank all the speakers for their very nice presentations and also the audience. And I remind you that tomorrow there is the second session that will be chaired by Professor Botana and Dr. Pisello. The session will be more on materials. Today it was more on structures. Tomorrow it will be more on materials, still from different perspectives. So there will be the structural analysis part, there will be the environmental engineering part, there will be different aspects, the chemical aspects, and at the end there will be a talk presenting also the information communication technology platform developed within Heracles, so also multidisciplinary. Okay, thank you very much. With this I close the session and I say goodbye. Thank you.